Okay. So if equipment has been listed by a qualified electrical testing laboratory that is recognized, it shall be suitable for installation in the NEC code book. That will tell you guys that equipment, if you install equipment, it has to be listed. And when you install the equipment, you have to install it based on the listing, meaning that fuse and circuit breaker, they are listed, but we did not install it based on the listing. The listing says you cannot install it in an area where it exceeds its capability of fighting, and we went and we put it there. Approved. Approval. The conductor and the equipment required to be or permitted by this code shall be acceptable only if approved by the authority having jurisdiction. A couple of things, guys, about the installation, examination, identification, installation of use of equipment. Listed or labeled equipment shall be installed and used in accordance with the listing. You can see we just violated that one, right? A second ago, because we install it not according to the listing that says do not install. Here's a couple of places I want to move fast through these one. These are all the listing agencies, notoriously famous. One of them is the UL. The white book, how many of you guys have the white book? The white book? The white book is 2011. I should have brought mine with me. If you, anything in there's a really nice thing, the nice thing about the white book is it takes every article in a NEC code book. Say you have an ARC switchgear, and you want to know which UL listing does an ARC switchgear go under. So it takes the article of the NEC code book and the listing, the UL listing, and it references them. So if you're familiar with the NEC code book, you don't have to be familiar with this book, because all what you have to do is, for example, go to the panel section, right? Article 408 talks about panels, and it will tell you 408 exactly where the labels of all these panels have to be. It could be an MCC or a panel board versus a load center or a switch gear or a switchboard. So it's really a great way of referencing UL to the NEC code book. So these are all testing agencies. We went to town with these. So I'm going to move directly through that one. So when it comes to circuit breakers, guys, probably a lot of things: loose connection, over torquing or under torquing. The logs on a circuit breaker is a common mistakes that can lead into arcing and sparking. So the circuit breaker that's supposed to be your valve for protection becomes a source of hazard by over or under torquing or not properly maintain the torque on these circuit breakers. So you say, Chad, how are we going to maintain that torque and how often we need to torque them? That's where this document becomes really good and handy. It will tell you how often you have to go torque these logs on the circuit breakers and so forth. The 70B. Okay, I don't know why they call it a branch circuit overcurrent device, but this is how the NEC code book, guys, defines an overcomputation device capable of providing protection for, and this is kind of interesting, for service, feeder, and branch circuit. So why do we call it branch circuit then? I don't know. I've been thinking about that one. Anybody knows why we call it branch circuit when it provides protection for branch circuit, feeder, or service, and equipment over the full range of the overcomputation device between rated current and its interrupting rating. Branch circuit protection provided interrupting rating. Here's the minimum use, but not less than 5,000. Let's go directly into an interesting one I'm going to show you. Here's a project that I do with my students. Neil, you're familiar with that one. An industrial project. 4,000 amp switch gear, arc flash analysis on this project, and overcurrent detection coordination. So I'm just the sheet that I gave you guys is how to calculate the short circuit in a power system by hand. Good luck doing it in a bigger system because it takes forever to do these calculations by hand. There is a software. How many of you guys are familiar with SKM? I know Neil, you are. Anybody is familiar with SKM, PTW, Power Tools for Windows? This software is like 50 grand in the market. You buy all the ins and outs of it. It does arc flash analysis, DC analysis, AC analysis, single phase analysis, single phase system, starting 1500 horsepower motor. The cable, the voltage, and what do you need to do to start it. So arc, everything. I'll show you how it does the arc, but what I want to use it for really is to explain what an overcome detection device is. And if no changes. Okay, so here's a circuit breaker, guys. I use Cutler hammer, I believe here. We're using Cutler hammer. Yep, Magnum D. How many of you guys have worked with like a 4,000 amp switch gear? Familiar with the power circuit breakers? Power circuit breakers? No. Okay, here's a power circuit breaker. This happened to be Cutler hammer, Magnum DS RMS 520, long time, short time, instantaneous, 4,000 amp frame. So this is the curve that comes with it. So when I provide protection, I don't know if I can. When I provide protection, they say over the range of the current that can be encountered. Over the range of the current that can be encountered. Look at the green thing here. I have to provide protection. This is the highest short circuit that this circuit breaker is going to see. I need to protect the system from this point all the way up to this point, which is the full load current. Does that make sense? This is my full load current right in here. And this is my three-phase short circuit value. And my protection have to be over this range from here all the way to here. That's the range when they say circuit breaker have to provide a protection over range of the current encountered. That's what they mean by the range. And that's happy to be a graphic, guys. You're familiar with this one. If you so this is this section here, the top one is called long time pickup. So I'm sitting at my circuit breaker at 1. If I go sit it at point 0.4, now I have just changed the circuit breaker into what's 0.4 or 400, 4,000, whatever 0.4 or 4,000 is. Long time pickup. This is for if you have, guys, a ground fault. That's long time delay. It delays the overload of your system. Short time pickup. This component here will take care of the ground faults and low level three phase. And the last one is the delay. That will take care of delay the ground fault and the short circuit values. How much you want to delay? I want to delay at 0.5 of a second on the system. So what this means, guys, is a range from right in here all the way up to here is what we're trying to protect. If you look at the blue one, the black right now, so the range that I'm protecting is from, it looks like from 100,000 right here all the way up to what looks like down here, maybe it's 800 or so, 800, 900. That range, the circuit breaker should be able to protect my equipment. This happened to be at a chiller, protecting a chiller. So that's what they mean by a range. Anyway, so that's, and I'll be referring to these as we go. So when you hear them talk about branch circuit over the full range of overcurrent between its rated current and its interrupting current, the rated current, guys, the 800 amp like I showed, all the way to the interrupting current, which is a 200,000. Any comments, guys? Any questions about that one? The range, I thought, because the most confusing things for the people is the range. A few things about sizing overcome detection device, guys, is the major thing is continuous load. If you have a continuous load, you have to oversize your overcome detection device 25%. Okay, overcome detection device. If it supplies load, continuous and non-continuous load, you multiply the continuous by 1.25, the non-continuous add them as is, and you size your overcome detection device. That's what this is telling you. So if I have a load 100 amp, continuous load, and another 100 amp non-continuous load, the continuous becomes 125, add into 100 becomes 225, the size of your overcome detection device will be 225. So that's That's as simple as that when sizing the overcome protection device for equipments like heaters. This is typically for heaters. Same thing for feeders, guys. For branch circuits or feeders, same calculation, the 125 and the 125 for both feeders and branch circuits. A couple of definitions for a breaker. So this is defining what a breaker is: device that can either manually or automatically interrupt the circuit. So manually you can turn it on and off, or under on a fault condition it will trip and to protect the circuit. So that's open and close a circuit by non-auto, which is manually, and automatically on a predetermined value without damaging itself. When properly applied, it will interrupt the circuit under ground fault or short circuit condition. That's like you guys know, you can go use it as a switch, or if you have a short circuit, it trips. Really no. The only difference, the only thing that confuses people with circuit breaker is they have a range. So why did it take my circuit breaker that long to trip when I have an overload? Because it's a range. It sits there, it has to heat. If it's thermomagnetic, that's the delay. There's delay in it. So adjustable as it applies to the circuit breaker. You guys have just seen an adjustable circuit breaker a second ago. Here's you're looking at an adjustable circuit breaker. Can you guys see I can move? Can you guys see how I move that figure here? I'm adjusting the circuit breaker up, and I'm adjusting it this way, and I'm adjusting it that way, and I'm adjusting it, and I'm screwing basically it. That's called an adjustable circuit breaker. You grab a screwdriver. Don't do that, because you need to do some calculation before you start messing around with it. With your screwdriver, and you start adjusting these dials on the face of a circuit breaker. Before you do that, be very careful, because there's overcome protection coordination that happening between above and below stream of that circuit breaker. Otherwise, you can alter the coordination and make the circuit breaker trip faster than it should, or slower than it should. Either case, if it's faster than it should, a nuisance tripping. If it's slower than it should, you create a fire, and then the circuit breaker will wake up. So if this is graphically, guys, moving it, if you don't want to move it graphically, here's where you adjust it. Can you see the long time pickup? That's the overload component. Long time delay, that's how long do you want to delay the overload. When you overload the circuit breaker, do you want it to trip within 4 seconds, it starts from 2 seconds, or 24 seconds? That's what basically, and the minute you have put 24 seconds, that circuit breaker will trip, will wait 24 seconds before it trips. So then short time pickup, that's your ground fault and short circuit. Same thing, how long you want to short time pickup delay it, and at what value do you want it to pick up. So if you guys look at this, if it sit at 10, just very quick, if it sit at 10 times a long time pickup, so if your circuit breaker is 100 and you set it at 10, it will trip at 10 times 100 is what? 1,000. At 1,000 amp, it will trip within 0.5 of a second. Does that make sense? So that's what an adjustable circuit breaker is. If you've never seen this, if you worked on 1,000 amp or more, 99% of the time you've seen some adjustable circuit breakers. It doesn't make sense to put them in anything less than probably 400 amp or maybe 600 amp, especially the long time and the short time. Okay, so that's what an adjustable circuit breaker is. I think I have an unadjustable one. Where am I here? So just to give you an idea. Okay, Chad, right here. Okay, no, not this. Curves. I don't know. No, all these are adjustable circuit breakers. I'll show you as we go on unadjustable. So that's what your adjustable circuit breaker explained by an engineer. Right? Because I'm sure a lot of you guys have seen adjustable, what the heck, or maybe you've seen them around, but that's how when you work in a hospital and you have to overcome coordination, that's what the engineers do. You grab all these curves, but then as long as they don't touch each other, you're good to go. They overlap and touch each other. This means the ground fault right here in this panel will trip a 1200 amp switchboard. Is that good, bad, or ugly? That's an ugly. right? Especially if you're in charge, you know. So that's your adjustable circuit breaker. Instantaneous trip. Instantaneous trip, guys, meaning if you hit this point, you do not delay. There is no delay in the system. I'll show you the instantaneous trip as part of this circuit breaker right here. Do you see that box here, right here? That rectangle? That's called instantaneous. If I have a short circuit, looks like it's starting based on this system here's at 1,000 amp here, 1K, 2,000, 3,000, 4,000, 5,000. If I hit the 5,000 point right here, my circuit breaker will instantaneously trip. What does that mean? It will trip within, this is 0.1 of a second, so this is 0.01, 0.02, 0.03, 0.04, 5, 6, 0.06 of a second. Can you guys count or memorize a 0.06 of a second? And that's called instantaneous. Any comments, guys? Any question about instantaneous strip circuit breakers? So that's the circuit breakers the instantaneous strip circuit breakers. Instantaneous strip circuit breakers, guys, we like to use them on. How many of you have heard motor circuit protector? Dollar Hammer use them. Motor circuit protector. I'm sure Jeff yesterday talked about motor circuit protector. When you have motors, you know, you have your disconnect, and then you have to have your overload component, which is a fuser circuit breaker. Then you have to have your controller and overload, right? So instead of having a circuit breaker, they have a motor circuit protector, which is just looking at the short circuit, not the overload. Why the overload is not an issue on the motor? Because you already have an overload component. So that's coming on motors that they use an instantaneous strip only circuit breaker. Instantaneous strip only circuit breaker. Inverse time as it applies to the circuit breaker, guys, and non-adjustable circuit breaker and setting of a circuit breaker. These are all directly from the code, and the easiest way is just looking at it here from the curve, really. Here's my curve. Inverse. Can you guys see how the curve goes down here? I wish I could draw on that one. The higher, if you move right here, this is the amps, this is the time. The higher the amp, can you guys see the higher the amp, the faster the circuit breaker will trip. The higher the amp, the faster the circuit breaker will trip. So if I have a 500 amp ground fault on my system, it will trip in, say, 1 second. If I have 1,000, it will trip in half a second. And you can keep tripping faster and faster. That's called inverse type circuit breaker. The higher the amp, the faster the circuit breaker is. Can you guys see that curve is going down, right? So that's inverse. Settings, we talked about the settings, guys. These are adjustable settings on my circuit breaker. If I go change this one to a non-adjustable circuit breaker, show you a non-adjustable circuit breaker, QB. Do you guys like QB? QO? QO? Okay, so let's go take device and go to the library. QO is square D, right? QO, let's go to square D and get a QO, because you guys are familiar with the QO, is a square D here. Here's square D. And we need to do thermal. That's the type that they use, because these are the cheapest thing that you can get, right? And okay, thermal, and we're gonna go to just show you very quick here a square D here. Okay, so Q, where's my Q's? Okay, we're up, we're going the wrong direction. So square D, no. Do you see any Q's, guys? Am I didn't go, or am I think I'm losing. Okay, here you go. Q's. Okay, Q, QO, Q. Okay, so we have QOs. Here's a QO. 3-pole, QO 3-pole, right? 15 to 20 amp. This is how it looks like. That's the curve. This is your 15 amp that you put on your circuit, on your lighting circuit, QO. 3-phase. Again, you can put single phase, but let's just say 20 amp because the most common. Here's a 20 amp. That's how it looks like, the curve. What does that mean, guys? If you have 15 amps, within, you exceed the 20 amps here, it will take a while until to trip, but it looks like it's rated for, here's 100, 200, at 300. If you put close to 300, maybe 150 amp out of this circuit breaker, it will trip instantly. But if you put 100 amp out of the 20 amp circuit breaker, look how long will it take it to open. Can you guys see that? Cool. 100, 100, 100, up to close to what? 1 second to open. That's what they call it, non-adjust. Do you see anything to adjust here on that? That's what you call dumber than a rock circuit breaker that you can buy. Nothing. It doesn't really, what you see is what you get. Any comments, guys? Any questions? Inverse type, you can see the curve is going this way. The higher the amp, the faster it trips. Weld and doesn't open. Siemens took over them. Yeah, I think they might have them under obsolete. They have softwares here. They have obsolete in the software just because if you go into an area and you need to coordinate with them, you know what they are, but they call them obsolete. So this is, guys, non-adjustable circuit breaker. Can you see anything here to adjust? What you see is what you get right here. Either 20 amps or none. Nothing, no setting. So that's compared to this one. Compare this one to this is power circuit breaker adjustable. Can you see how many adjustments you can do on that circuit breaker? You can make it. You can look at that. You can move it up. You can move it down. You can really adjust it. Look at that. Pull it down. Pull it up. Every time you do that, you alter the characteristic. You basically create a new circuit breaker. Every time you adjust that one. Arc flash. Do you see the whole arc flash and your PPE? That component here at the bottom, that's responsible for your arc flash level. How much arc flash level? So let's just reduce the arc flash level, guys. Try to reduce it on the circuit breaker. If I move this way, less arc flash. If I move that other way, more arc flash. So these are a major part when you start dealing with the circuit breaker. So now I have a huge amount of arc flash. I moved it up. I delay it. You bring it down. It opens fast. You minimize the arc flash condition. Okay, so we got you the QB and Magnum DS, the cheapest and the most expensive circuit breakers in one sheet. So that's just to get you. A lot of us, guys, you read the NEC code book and see adjustable and move on, right? There's a whole lot of things related to the word settings and adjustable and non-adjustable related to them. Coordination, selective coordination. You heard about this one all the time. You're not supposed to do that, right? You're not supposed to go change the balance on this energy, right? The rule working energy is based on 7D and OSHA. Working energized is the exception, not the rule. The exception is if you have to have a reason for exception. Hospitals, for example, I can't shut down the circuit feeding because it's feeding a hospital, a bed, patient bed location. You know what I mean? Or if I shut down, there's a nuclear reactor that's going to explode. There's nothing there to explode, right? These are but it's inconvenience. It's not one of them. Because I'm lazy like Chad. I don't want to go run and find the circuit breaker. Anyway, so if you're to work on this one, guys, easily ground fault, a hot touch the frame of the fixture, trip the 1200 amp switch gear. Bad news. How could that happen? Because you don't have selectivity or coordination. That's where the word selectivity or coordination. You have a ground fault, you need to localize the interruption of the power right at the location of the ground fault. Meaning, the ground fault is in this branch circuit. The only circuit breaker that should trip is the 20 amp circuit that's feeding this circuit breaker. So that's where the coordination and the overcomputation device is. Here's an example of selective coordination. I was just showing you a couple of curves, guys. Here's a 90 amp and a 400 amp. A 90 amp branch circuit fit from a 400 amp. So right now, let me just use my. Right now, if I draw the circuit here, the one-line diagram for this boy, here's how it looks like. It looks like we're feeding a load here, whatever that load is, with 90 amps, right? And the main of this panel is 400. So we send one of you, my friends, to go work on this machine, and you made whatever happened, and you shorted. Ground fault, or 85% of faults are ground faults. Or you decided to put phase A and phase B and flip the switch time together and why or not. You know, could that happen? Not a whole lot, but okay, so which one do you think is going to trip? Should trip, the 90. Based, here's the curves, guys. These are fancy curves for nothing. All what you're looking for, are they touching? Wherever they touch each other, there's miscoordination. That's it. So look at them from top to bottom. Are they touching? The only place where they're touching is right here, overlapping, right? So right in here, can you guys see that area right in here? This is all hell break loose. All hell break loose, meaning if you have a short circuit in this area that high, it looks like start at 100, say 1500 multiplied. Okay, so this is, I'm sorry, 1000, 1500. Start right here at 1500. At 1500, if the short circuit is 1500 or high, it's a race between which circuit breaker is going to trip. But to get the 1500 though, two things could happen in real life. You almost have that fixture and that panel that feed the fixture have to be right directly next to the service. Very high short circuit next to the service, closer to the service. Or you went to phase A and phase B in a J box and you tied them together on this three-phase equipment and you flip the switch. So 90%, and I say 90, I would say dare to say 96 to 98% of the time, guys, you have full coordination. 95% of the time you're going to be in this range. So the 5 to 4% of the time, all hell break loose, and it's the rest that you're going to have. Granted, most of your ground fault, which is the most offender, guys, the most offender are 85% is ground faults. All your ground faults are right here in this area. These are only when you have face to face or face to face to face. That's when you are in this area. So, any comments? Any questions? It's like with the insurance companies come to you and they say, well, what if somebody walk in on your lawn and they trip and they go sue you? That will be probably part of the 5%. Could it happen? Absolutely. How often does it happen? Does it happen to anybody in this class? Somebody tripped on your lawn, break their neck, and sued you? Never heard of anybody. It did happen though. So that's the 5%. If you want to get 100%, then you have to use a different circuit breaker. With these two circuit breakers, you cannot coordinate them. Okay, here's if you're a busman, if you use busman, guys, for years, and you're not fancy like your friend Chad, and you have a software that you can look at them. Let me show you how they do the coordination best for the software. Very easy because you have it. And then we'll go to the ratio. So if you have a software, guys, very easy. As long as they don't touch each other, we're in a very good shape. So let's go to close this one here and go to the one. Okay, here's a 4,000 amp switch gear. I want to coordinate that one with a chiller. Here's my chiller. Can you guys see the chiller starting curve of a chiller? Right now, can you guys see the circuit breaker ahead of the chiller that protects the chiller, and the chiller starting curve is grossly undersized. Based on, can you guys see the blue and the black curve? Right now, the chiller will never start, right? Because where's the full load current of the chiller? Right in here. And where's the full load current of the circuit breaker? Right in here. So I have a chiller that needs more current than the circuit breaker can allow it to do. Would that happen? Absolutely not. So let's go change the circuit breaker. I can't change the chiller because I'm not a mechanical engineer. That's what you get is what right? It's there. It's not your job. My job is to change my circuit breaker. So here's what you do. We are having an 800 amp circuit breaker on that boy. So and we're sizing it based on 0.8. Look what happened is if I go put it on 0.1. Now I got myself an 800 amp circuit breaker, right? That sounds like I can even adjust it slightly lower, and still, can you guys see clear it? Up to this point, every time the chiller is going to start, because of the starting curve of the chiller here, the circuit breaker will trip. So you need to take this leg, can you guys see that, and move it. Move it as far. You move it that far, arc flash will burn you, right? If you have to move it as close to that red curve as you can without touching it. Why can't I just keep moving it to the left, right, Chad? Because you're having a lot of arc flash. Perfect. So here's the circuit breaker, guys, that protect the chiller, that allow the chiller to start and run, and at the same time allow it to start and run, which is all what you need. Now, this circuit breaker is fed from another circuit breaker, which is the main, the 4000 amp. Can you guys see that right at this point, they are overlapping slightly? In order to have 100% coordination, all what you have to do, go to the main and raise, can you guys see, raise the main enough to coordinate. You don't want to raise it too much. You know what happens if you raise it too much? Arc flash gets bigger and bigger and bigger. You're allowing the short circuit to sit and you switch gear for a longer period. You don't want to do that. Okay. Gentlemen, what you're looking at is a fully coordinated chiller overcome protection device, adjustable circuit breaker with the main that feed the whole building. Fully coordinated. Do they touch each other? No. Fully coordinated. When you're done with this, then you go to Mr. Electrician and you say, here's your report. You run a report, PCC report to the chiller. Great, you run it, and this is what you guys get. Override it, and you get a report like this, or something similar. Here's the report. Here's the settings that you need. Grab your screwdriver and go adjust the long time pickup, the long time delay, short time pickup, short time delay, instantaneous on this circuit breaker, which you see circuit breaker for the chiller at these values, and the main should be down here. And here's the information about the main. That's what you guys receive. That's what I say. Don't go set this one to 0.5, because you set it to 0.5, you screwed up the coordination. You screwed up the coordination. Any comments, guys? Any questions?
So that coordination and the chiller running, obviously that's the red line that goes all the way down the top.
That's the chiller running.
If there's a short, then that's why. Okay.
When there's a short circuit, right now, no, that red here, that little leg, that's a starting curve. That's a starting curve up to 10 seconds. Can you guys see 10 seconds? Your chiller's full load current looks like almost 1,000. No, not 1,000. So I can't. So 800. So it looks like an 800, right? Here's 100, 200, 300, 400, 500, 600. I can't even count. 1, 2. No, this will be 100, 200, 300, 400, 500, 600. Looks like 600 here. 600. Oh, it says on the bottom. I can't. 600. Full load amp is right. Full. Oh yes, thank you. Yeah, right here. If you put it right here, I forgot, man. There's so much. I forgot that. So right in here is 3. Right at this point here, 3656 is the starting current. So it allows for how long? For only 10 seconds, right here. So it allows the chiller to start, and when the chiller come up to speed, see how it goes this way to protect it. Any comments, guys? Any questions about that? Any comments? Any questions? So I thought give you a unique perspective. Okay, now if you don't have this fancy stuff and you use I always say, guys, if you don't have circuit breakers, fancy circuit softwares, and you maintain the ratio 2:1 on your circuit breakers, you're good. Meaning, if your main is 100, do not, the largest branch circuit is 50. If you maintain this, you maintain a good coordination. 2:1 ratio. Meaning the main is going to be twice as much as the largest branch circuit. Okay, so these are for the fuses coming from Busman, guys. They give you based on the type of the fuse what ratio you have to do. So if you're using low peak KRP-CSP and you want to coordinate it with the same type, two types are the same, see the ratio is 2:1, meaning the main can be twice as much as the branch, meaning a 2000 amp can feed no more than 1000 amp. The largest is 1000 amp. And then I'm not going to go over all of them, guys. You can go as high as 8:1 if they're two different type of fuses. But typically, guys, is if you have the same type of fuse or the same type of circuit breakers, 2:1 will get you a reasonable coordination. You get higher than 600, I would say maybe 800 to 1000 amp, you better do some coordination. Really, you have to run some coordination with circuit breakers, especially with circuit breakers. Any comments, guys? Any questions? Any comments? Any questions about that? So that's my coordination. Remember that low peak time delay fuses. I wanna flash this one because I thought that was really cool when I was looking at it. You guys want a quick break? Yes, no? Shall we? Okay. Let's take a quick break. How about that? I know it's after lunch and it settles down a little bit. Friend Chad, when you have a chance. It's hard these days. Okay, this is from Buffman. When it comes, I wanted to show you something before I go there. I wanted to show you guys, Bussman has some really nice, I'm sure you, I think it's page 208, 208. Okay, maybe not. 28. What is it? Okay, here you go. Yeah. So let me just flash this one, guys. My friends from Bussman will be happy because we use their stuff anyway. This is the reason why we have our competition device. That's directly from Bussman book. When you guys, this happened to be a 10 horsepower motor running at 460 or rated for 460, and you have a branch circuit that this branch circuit is going to protect the motor and protect that motor, and it happened to be the branch circuit overcome protection device happened to be we don't have it here, but we need an overcome protection device to protect it. So I want you guys to look at the legend here to understand it. You see the green is motor start. Can you guys see the motor will start right in here, close to, I don't know what, 10 amps maybe, 12 amps, 10 horsepower at 460 probably. How many amps is 10 horsepower at 460? 10 amps. I thought so close to that one. So this is the full 12 amps. Yeah, there's a 12 amps here. That's then when you start it though, it pulls close to 90 amps. Can you guys see right at the bottom here? It pulls up. That's the starting up to almost 10 seconds. Then it goes back to normal. That's the starting curve on an induction motor, design B induction motor, typical, right? So that's what you need to protect the motor and allow it to start. Okay. I don't know how many of you guys have seen the overload relay. Can you guys see that blue? The blue stuff is your overload relay. Yesterday, my friend, you guys were talking with Jeff. That's what Jeff was doing with you. And we were sizing the overload based on 115 or 125, right? Based on the service factor. So this is, I believe, it's sized based on 115, right in here, my overload. Then motor damage, that red line here, if the current reach that red line, the smoke and the fire will be coming out of the windings of your transformer. That's meaning all hell break loose, right? So you're having a fire inside your motor. So that's, you don't want to reach this. Then you go into the number 12, wire damage. I don't know how many, I'm sure a lot of you guys know, equipments as well as conductors have 2 amp ratings. Amp rating is how much continuously they can carry a current. That's the ampacity of the conductor. We all know that, right? Based on the temperature and the bundling. Number 2 is the withstand rating, meaning if you have a short circuit in this conductor, would this conductor be able to withstand the short circuit or the ground fault long enough for the fuse or the circuit breaker to open the circuit and de-energize it? Or would it turn into little pieces like we saw? That's called the damage curve of the conductor. It's a function of how thick the conductor is it copper or aluminum, and what type of insulation do you have around it. Okay, so long story short, do you see that line here? That yellow, that's all hell break loose. The conductor is on fire when you reach it. Thermal withstand limit. This is the thermal withstand limit. That little bottom here. Your overload protection, electronic overload protection. If you have a short circuit, the overload protection will be fried at a certain value. So that if you reach that little level here, your overload that's supposed to protect you from overload the motor, it will be fried because too much current went through it because of short circuit. So now you have to protect the overload from short circuit, not just the motor. Contactor breaking current, that's that value here. Contactor breaking current, that's if this amount of current to go through the contactor, it will wield it. So you don't want the current, that short circuit current going through the contactor, the starter, your magnet starter. So you want to protect the contactor too. And the last one is contactor withstand. The withstand capability of your contactor is right here. That's how much your contactor can handle actually without blowing up the contactor itself as you move short circuit current through it. So anyway, when you provide overcam protection device, guys, a lot of us, there are 2 types of protection. Protection number 1, here's the type 1. Type 1 to protect the people. So if you have a short circuit protection and you have type 1, you have a short circuit, the fuse will open, but the magnetic contactor might be fried. The VFD gone basically. Nobody got hurt, nothing exploded, but we fried the controller. That's an acceptable level of protection on type 1. You might have to take the contactors and clean them and adjust them and so forth. That's on type 1. If you go to type 2, which I believe in Europe they use a lot of type 2, or if you use a IEC system, the contactors, they need type 2. Type 2, you have a ground fault or a short circuit in the motor, the load side of the motor controller. All what you have to do is fix the problem first. Why are we ground faulted? Why do we have a ground fault, or why do we have a short circuit? When you're done fixing the motor, what was the reason for the ground fault? Then you're supposed to change your fuses. Typically, it has to be fuses, and everything should be okay. You might have to minor damage in certain equipment, but your equipment might survive. Anyway, so that's this one. So I'm going to show you a couple of curves. Here's curve number 1, guys. This is a fast-acting fuse. If you use a fast-acting fuse, you size it based on 300, right? Remember the NEC code book says, yesterday you guys did this one with my friend Keljik, right? 300 if it's fast-acting non-time delay fuse, 175 if it's dual element. So look at this. This guy protects you from type 2. Get you type 2, yes. Single phasing, yes. Backup single phase, no. It doesn't provide a backup single phase. Backup overload, no. Meets 110, yes. Meets the protection of the conductors and so forth. This is just to protect the branch circuit and the motor. It protects them. So it doesn't provide a backup overload protection. Can you guys see the overload relay here? It's not providing a backup protection for the overload or a backup for single phasing if you single phase. Anyway, again, this is done by Busman. I want to take you, there's a bunch of them. The last one is probably the most important one, this one. Here's what they recommend for you: dual element time delay fuse, class RK1 or J. How many of you guys use fuses on motors? Use fuse on motors? That's why a lot of people use fuse on motors. So if you use an RK1, so this is, look at the curve, how it curves, the shape of the curve. Right at this point, guys, this is a backup protection for overload. So if your overload is to malfunction, you're not going to burn your equipment. You have a backup overload here. So supposedly this is the best and the brightest one. It's a low peak dual element time delay fuse. That's the type that they use. It provides. Can you guys see right here this curve here? This is what did we call this? Is contactor withstand. That's when your contactors weld together. If you reach that level. Now see that fuse is going to open before you reach that level. Look at the yellow. The yellow is when your conductor starts smoking. Can you guys see that this fuse will protect you from that one? This is the damage for the overload. So long story short, it's going to allow your motor to start, and this is the damage for the motor. I don't know if you can see that curve here, motor damage curve. So the fuse will open fast enough to protect you from damaging your contactor or your overload or your motor or your conductor because of a short circuit or ground fault protection. Yes, sir. Well, they can't, they're more, I think they're less, they have more, their tolerance is less than the circuit breakers, because circuit breakers are mechanical action, it needs to heat sub. So when they give you that thick curve, we really don't know exactly when it's going to open, but we guarantee you that's going to open between this value and this value. Plus or minus 10, 20%, above and below, that's when the fuse is going to burn. Same thing with circuit breakers. When they give you that thick, why don't they give just one line? Because the manufacturer can guarantee between two values. So that's the best that you can get. When you see that thick, we're guaranteed between this value to this value, we're going to open. Where on them, it depends upon the characteristic of the curve and so forth. So, but you can see if you can, but you deal with the whole thing. As long as the whole thing clearing, can you see the whole thing is clearing out? Right in here, my damage curve here is into the, my damage curve is inside the fuse here. So you can argue is the fuse, with the fuse open before the smoke start coming out of my circuit breaker here. So I would like to see this curve move this slightly to this side on the damage curve side. So, but that's supposed to give you the protection type 2 for all these things that could happen in your power system. And there's a couple of things, guys. Look at the circuit breaker. Here's the circuit breaker, for example. That's the one that we just looked in QB. The one that we looked at it, very similar. I think it's QB, the one that they're using here. They size it like you guys did with Jeff yesterday, 250. Look at the QB. The QB even is not protecting your motor. The damage curve, I mean, if there's a heat, it might not even protect your motor windings. These are windings of your motor. If you size it that fast, actually it's not protecting even. Now remember, this is manufacturer fuses talking about circuit breakers. So maybe you just be very careful. You definitely will find another circuit breaker that do a better performance than that. So they chose because gosh, even the conductor is not protected. Why would anybody put, look at the conductor here is not even protected from a damage curve here. Definitely the contactors are not protected right here. They will be burned, some of them. So, but you met the code though. You protected the motor and you size it best in 250. But yeah, this is a bad application of that circuit breaker. Any comments, guys? Any questions about that? Here's your circuit breaker. Here's another different type. This is instantaneous strip circuit breaker. Did Jeff talk about this one yesterday, guys? When you size, that's where you size based on short circuit only, no overload, nothing. This is set at 700. We can set them up to what? 800. This baby is really good. It actually protects you. It looks like the conductor for the most part, the contactor. That's why Cutler hammer use it a lot. But what happened to the motor here? The windings. The windings might fry. Will fry. So anyway, looking at all these guys, supposedly your best performance, and rightfully so, is certain fuses size to protect guys. It will give you the lower one here. That guy is shaped. Is shaped to provide you the as much protection for as many of these components as you can. Any comments, guys? Any questions? So I thought just to show that one for you, show you the protection. So when you have a fuse, it's not enough that you need to protect your conductor, your contactor, your overload, but also the windings if it has a motor, or a heater or a lamp. You need to protect the ballast that cooking this lamp here. Okay, because of all of this, guys, then you get into low peak time delay fuses. That's the one that we were talking about, low peak time delay fuses. Look how they achieve that. With that, what they do is they open, here's a low peak main feeding another, that's the main feeding another one, and so 3 circuit breakers in series with each other. This is a branch circuit, this is a feeder, this is a service. All of them are low peak. So what they do when they have a short circuit, guys, the problem with the short circuit is there's this huge amount of energy. I can make this huge amount of energy that burn, that shake and bake my equipment. I make it shrink by opening the circuit breaker fast or the fuse fast. The problem with circuit breaker, they're ready to open within 3 cycles. But you have 3 cycles, 3 over 60 is what? 1/20th of a second. That's how they should open within 1/20th of a second. Now the fuse guys, they come and they say we can open within a quarter of a cycle. Remember, 3 cycles versus a quarter of a cycle. That makes a big difference. The faster the fuse open, the less energy will cook, shake, and bake your equipment. That's what the whole current limiting low peak type the fuses happen to be. So here's where opening here. This is the amount of energy when you open within a quarter of a cycle or half a cycle, guys. That's the amount of energy that you leave. That this first one, so this guy is going to let through this amount of energy, right? Now this guy is going to only see this amount going through it because it got limited, and then it's going to limit it again. Can you see that? This guy is only going to limit it to lower. And the third guy is only going to see this amount going through it, and that guy is going to limit it even more. So long story short, they depend on that limitation of the energy as it goes through the overcapacity devices to get you a tiny little shake and bake happening at the source of the short circuit or the ground fault. That's why they can protect the motors and they protect the contactor and they protect all this good stuff by limiting the current and by opening fast. Any comments, guys, about this? Any comments, any questions? So by far, if you know, circuit breakers are great if you have loads, if you have lighting load, receptacle load, they're superior, panels and all this stuff. When it comes to machines and protecting controllers, a lot of fuses are very good protection. Protect the VFDs and the starters and so forth. They're a better protection for your control system, so to speak. Any comments, guys? Any questions about that? Questions, comments? Limiting it. Okay, electrical system coordination. We talked about this, guys. An orderly shutdown of you have to is required to minimize the hazard. A system of coordinated based on the following 2 conditions must be done. Coordinated short circuit protection, overload indicating based on the monitoring system of the device. So this is just telling you, you have, you know, if your system, unless it's create a hazard, you have to provide where an orderly shutdown is required to minimize the hazard. you have to provide an overcurrent protection device coordination. So a good example of this, the hospitals. Do you really want to mess around with a fixture like this and then trip the main on a hospital? Right? Chemical manufacturers must coordinate, because you mess around with a circuit and you trip down a chemical process that could ignite or make problem hazard. So a building like this, do I need to have a coordination for the power system for the building like this by code? I don't need to. Would you be smart to do it? Yes. So, but the code require it to minimize the hazard. The emergency system require coordination. All your lighting system for emergency system and fire pump and elevators that use for emergency must be coordinated. Other than that, so minimize the hazard and emergency system, legally required emergency system and legally required standby system require it. Other than that, it's optional to do the coordination. Ground fault protection of equipment. The ground fault, guys, this is the most confusing part of why is ground fault. The ground fault for up to 1,000 amp, perfectly fine to be part of the circuit breaker. The ground fault protection can be easily achieved by the 3-pole or single pole or 2-pole circuit breakers or fuses, up to 1,000 amp. Higher than 1,000 amp equipment, branch circuits, feeders, or services, you go higher than 1,000 amp, the ground fault become low enough that cannot be seen by the circuit breaker or the fuse, but high enough that they can create a fire inside your building. Who cares? The smarter than Chad say, wow, at this level, I can have an 800 amp ground fault coming on a system that's 1,000 amps, and the 1,000 amp switchgear is looking there and watching it and thinking it's a load. When it's in reality is a ground fault and cooking and burning and arcing and sparking. So long story short, my friend, smarter than Chad decided that if you have a grounded system, you have to have a grounded system. Otherwise, the ground fault doesn't do a whole lot. And 277, 480, that's the most powerful voltage that we use. It pushes a lot of energy. It burns a lot of equipment. And 1,000 amp or higher, you're required to provide a device, a separate device or a function inside the existing device that you have. So it could be a function in the power circuit breaker or a separate device in addition to the circuit breaker that only looks at the ground fault and only trips or alarms at the ground fault situation. So because it becomes so high and so important, guys, that you need to look at it separately. Okay, so damage line to ground fault by operating or cause a disconnect to open all ungrounded conductor of the faulted circuit. This protection provided current levels less than those required to protect the conductors from damage through the operation of the supply circuit overcurrent protection devices. Interrupting rating, guys, the highest amount of current that a device can handle without blowing itself up like you saw in that system. So that's my ground fault. So that's a few things, guys, about the ground fault. I'm just going to show you a ground fault protection, how it looks like when you bring a ground fault protection. If you bring a device, let's just see a device. Here's a device here. I'm going to call it ground fault. And I'm going to go load it in the library. I'm going to bring a ground fault for this system and go to the library. It should get me a ground fault protection if I remember. Here's a ground fault. Color hammer, huh? So let's do a ground fault Magnum DS. Okay, Magnum DS. Let's do this one. 8,000 amp to a 6,000 amp frame. Grab that. Minimize it, and so that's ground fault protection. Where did it go now? Here's my okay, Chad. I know where my ground fault protection curve there. should have, there you go, is a ground fault. Okay, bus voltage must be greater than the 0. Oh, we didn't put the bus voltage here. Okay, here's your bus voltage, buddy, old Bell. Good, there you go. Put your bus voltage. Here's the ground fault. That's how it looks like, guys. This is my bus volt. Here's the settings. I'm setting my bus volt. I'm going to set it at 800 amp. So that's an 800 amp ground fault protection. Can you guys see how it only looks? And I can adjust the pickup, the delay on that one. So now if I have a ground fault on this system up to 800 volt, this will trip. If the ground fault on the system hits 800 amp. 240. Did I use that's a ground fault though. That's for your ground fault. I'm using a weird voltage, but you get the message, guys. We're using a 480. Okay, so we can use, not a big deal, but that will give you, that's nothing to do with the ground. This is just looking at the ground fault. It's not looking at the chiller in any way, shape, or form. It's looking at a ground fault in the chiller. There could be a ground fault in the chiller. Only it looks at the ground fault. It doesn't look at the phases. So when the chiller starts, the inrush will be seen where? Through the phases. That device will not see it. That one, the device goes, the inrush goes where? Through the phases, not the ground. Why should the inrush go through the ground? Just through the phases. It wouldn't be seen. This is looking at the phase, guys, phase A, phase B, phase C, and the neutral, and saying how much current is going back through the ground. So if you have a ground fault, the current will go, more current will go through the ground. So it calculates the current that goes in the phases and the current that goes back on the ground, and it trips if it's higher than the predetermined value. Okay, so that's your ground fault, and typically required in hospitals anywhere. You're required to have 2 of these, and they have to be at 2 levels and coordinated. Any comments, guys? Any questions about the ground faults? Talk about the ground fault protection. So we got the ground fault, interrupting rating, that the highest amp that the circuit breaker can interrupt. Here's that value. This is the value that this circuit breaker can interrupt without going into pieces right here. In this case, the rating of my my equipment. This one, guys, talks about the short circuit withstand of copper conductors. And for this, we talked about one thing I want to bring here and show you, the damage curve for the conductor. So we don't see any conductor here. So let me just, if you guys don't mind, I want to go to my chiller, if I find it. Okay, haven't looked at that for a while. It should be right here. I believe this is the curve oops, no, right here. So this is that feeder for the chiller. I'm going to take it and see, would that feeder burn if I have a short circuit in it? So you take it to and coordinate it with the branch. Okay, so can you just see that one? Here's my feeder for my chiller feeder. And here's a damage curve. This is a damage curve for the chiller. Here's the circuit breaker that would take the chiller. Can you guys see that this conductor is not protected right in this area? Right now? It's not protected right in this area. So you might have to lower, and you have an issue because if you keep lowering it, I don't know what size we're using conductor here. Cable. I'm using 2/0. At 2/0, based on this, it will burn right here, or it will be damaged. So I'm going to go 2/0. Do I have, that was a grossly undersized. What did we say the full load current of the chiller was? 600. I should have 2 sets though. So 600 divided by 2, that will give you 300. 300. How much will give you? 500 kcm. 2 sets. 500 kcm. So that's how many sets? 2 sets. That was grossly undersized. So here's the curve now. After you size it properly, you can see the curve move to the side. So The only time that might, if you reach this point right in here, it might be an issue. Here's an 860 amps for these. That's not bad. Any comments, guys? Any questions about the damage curve? Any comments? Any questions about the damage curve? Protecting, which means if this circuit breaker is not to open, then this circuit breaker will start smoking. And this conductor, but that's the least of your problem because the chiller probably will be smoking as well, at that time. So the damage curve, remember the word damage curve, that conductors can handle. For my conductor here, I have, like when I was looking at it here, I have 860 amps out of these two sets of 500, right? That's full load amp. But for a damage curve, they can handle, let's just look at this value. How much is this value? 164,000 amp. They can handle it up to 0.02 second. That's your damage curve. And you can see they can handle, let's look at this point right in here. How much is this? They can handle like 14,000 amp up to, what would that be value? A second, 2 seconds, 3 seconds. For 3 seconds, what do you say, 114,000 amp? 140,000 amps for 3 seconds. That's your damage curve for your conductors. And they can handle 860 amps forever. The two of them together. That's your full load rating of that conductor. So, all right, so who cares? When you come about these, it doesn't happen often, guys, in our industry, and the high voltage industry is a big deal. The setting of the circuit breaker will determine the size of the conductor. In the low voltage industry, 600 volt or less, what determines the size of the conductor is the full load current of the equipment. Then you multiply by 1.25 if it's continuous load, size your conductor. In the high voltage industry, where the short circuit is a decisive factor, you have to look at the short circuit too. So for example, look how this can change easily. I have a short circuit calculation. So this is, by the way, instead of using these curves, the software will take care of all these curves that you see. If you don't have a curves, these are all coming from Busman, just FYI. So if you set your circuit breaker, guys, at this is short circuit in thousands. So if you are sitting at 40,000 amp, can you guys see that? 40,000 amp, and you're tripping the overcome protection device at 1 cycle, right? Can you guys see 1 cycle here? And that will get me size. Can anybody help me here? Size 1. So now you got size 1. Now, say I don't want to trip at a cycle. I want to go trip at 100 cycles, right? Because I am, I want to see what I can do. If you set your circuit breaker to trip at 100 cycles, can you guys see that? What size conductor do you need? Now I'm exaggerating here because nobody will set the instantaneous to trip at 100 cycles, guys. That's eternity. That's the conductor sitting there and being cooked. So what's the more realistic application? More realistic is 3 cycles. I don't have 3 cycles here, but I do have 4 cycles. So I'm going to go to the 4 cycle right here. So that will be somewhere here. What's between 1 and 2 watt? Between 1 and, that would be probably 1 watt. That would be 1 watt. So I went from 1 to 1 watt because a circuit breaker will trip in 3 cycles. Why? It's for the same load. That drives a lot of people nuts. For the same load. Because you size based on the full load current and also the withstand rating of the conductor. If you have a short circuit, you need to make sure your conductor is not going to burn. Any comments, guys? Any questions? Comments, questions? Was the motor yesterday more exciting? More stuff? Did Jeff give you any of his jokes? No, he didn't say any jokes. He was in a bad mood yesterday.
It was a rough day yesterday.
Rough day. Ouch. Yeah, that was at the U of M one time. I got hit in the back, and the police came and gave me the ticket. It's my fault. No, because his argument, I think he has valid, is I pulled in and I get hit from behind, but I have yield sign, and I'm pulling in high velocity street. I thought I looked. It was in January. The snow banks was that high. I looked, but I should have looked more. I really did. I mean, I pulled in and the guy was coming. I think he was speeding. Hit me and spin me in the middle of the street. But my Suzuki was operable at the end and his truck busted. But I got the ticket though. So I drove my Suzuki. Drove it home and his truck was oil coming out of him and they have to tow his truck. I couldn't believe it. I think the way he hit must have hit the corner of the Suzuki where the steel is. It went right through his radiator and oil, and unreal. And I got a ticket. Okay, so this is exactly what I was just showing you guys, except with the software, the withstand rating of the conductors. So here's my favorite. Let's take number 12 because we use number 12 all the time. This boy, look at that variation of how much current this boy can carry, based on how fast you want to open the fuse or the circuit breaker. Look at that. Typically, circuit breaker guys open within 3 cycles. So for 3 cycles, at number 12, conductor can handle 1550 amps. How many of you have thought that a number 12 can handle 1550 amps? For 3 cycles. What is the 3 cycles? 1/20th of a second. Because the cycle is 60 seconds, right? 3 divided by 60 give you 1/20th of a second. Now if you want to cut this to a 1 cycle, what's 1 cycle? 1 cycle is 1/60th of a second. Look how the value. And if you want to open within a quarter of a cycle, 7600 amps, a quarter of a cycle, that's nothingness. I don't know if we can measure a quarter cycle. I don't know how they even measure it. A quarter of 1/60th. Anyway, the fancy curve that I showed you, see why the engineers love the software? Instead of looking at all these numbers there, all these represented directly into that curve, all of them. You can see the higher the cycle is, the less amp the conductor can carry, or the higher the time. Okay. Then you get into the equipment ground conductor. Now, what happened to the ground fault? The ground fault is going to go back through the equipment ground conductor. So your equipment grounding conductor could be grossly undersized based on the short circuit in your building, and that's what gives you guys a couple of sizes. For example, let's look at number 12 again. Number 12 for 5 seconds. 5 seconds you can pull how much amp out of number 12? This is withstand rating. This is after this, the THR can start melting. If you reach this, start melting, you start smelling things first and start melting, and the copper will after that melt too. So that's 155 amp, number 12 for 5 seconds. And then I use ICEA guys here so you can see how they're comparing all these values together. I squared T guys, that's the amount of energy. If it's insulation damage at 150, that will get you how much in like for the same right here. That will give you how much energy. I squared T is the energy times. Remember, this is times 10 to the power 6. It looks like that's how much energy this conductor is going to handle if it's exposed to this amount, or it's rated to handle. Any comments, guys? Any questions? Any comments? Any questions? So what we do when we do coordination, guys, the feeders that are closer to the service, you run like exactly like I showed. Grab the feeder and put it on the coordination. See, make sure it's protected, and you document it. and then you just cover your butt. Design was, right? Because these sheets are, are good, but they're not. The softwares are updated regularly, and so forth. So withstand rating of the conductor is the equivalent ground conductor. Take this example. I have a 50,000 amp available short circuit on the line side of a disconnect for this boy, and I have number 10 conductors, size based on 250.122 copper. We needed to increase. Okay, so that's if you do that one and you look at it, guys, from a circuit breaker point of view, which is it's going to open within one cycle, you're going to damage this conductor. If you look at it, this conductor is going to be damaged. So you have to increase the conductor into 2 in order to protect it with a 60 amp non-current time limiting breaker. So of course we're busman. So what do? To limit the energy coming in here, because I don't want to size the equivalent conductor higher, you use a current limiting fuse, guys. Cut the opening by a quarter. By cutting it by a quarter, number 10 will survive because it's not going to see the full hit of the short circuit. So that's where it becomes a big deal, guys. Current limiting fuses and all this good stuff. Any comments? Any questions? Any comments? Any questions about that? What they forget to tell you that the 50 RMS value here, how much of it? That's a phase to phase though. So how often do you really have phase to phase to ground? So I don't know. I find it interesting here. But long story short, what they're trying.
What's realistic? If it's from phase to ground, what's a realistic RMS?
Half of this. Yes, typically half. Line to ground is typically half of line to line on the system. So and it happens 85% of the time. So I don't know. My advice is that on most of the systems you use 250.122 when you size the conductor. 99% of the time you're okay. It really is. If in doubt, what you really need to do, you take the conductor and put it on the software, if you have a software or something in the software and check it. But if you use 250.122, you covered it. You covered it. The reason why you really need to use a current limiting fuses here, which is, I don't misunderstand, I think they're a great application, is to have a better protection for your controller, for your magnetic starter, VFD, soft start, and in the process you're also protecting the conductors, definitely, but not just to protect the equivalent ground conductor though. So any comments, any questions, guys? Any comments about that? Okay, so you guys are familiar with the current limiting fuses. We'll talk about this one later on. I have another slide that talk about current limiting fuses. Current limiting fuses open fast enough that they basically limit the amount of energy, magnetic and thermal, that will be dissipated in the system. Okay, there's overcurrent and overload, and I can't get my students, and then we to know the difference between them all the time. You get them confused. Overcurrent, guys, condition can be an overload, a short circuit, or a ground fault. That's called overcurrent. If you hear the word overcurrent, you can have an overcurrent condition because of overload, or ground fault, or short circuit. A ground fault is phase to ground. An overload is a motor that's supposed to pump water, to a 2-story building, and you install it to pump it to a 5-story building. So you're overloading it. A short circuit, you grab phase A and phase B, and you flip the switch. Tie it together with a wire nut, and you flip the switch on. So the difference between the overload is a special condition of the overcurrent. Overload is only when you overload a conductor or you overload a machine. Meaning it's rated for a certain amount of amps, and you make this machine work hard enough to pull more amps than what's rated for. Same thing for conductor. The conductor is rated under its normal operating condition to carry 10 amps. You tie more loads at the other end and you make it operate at 15 amps. So when it comes to feeders, circuit breaker and fuse protect you from overcurrent protection device all cases except when it comes to machines that has motors. That's what you guys covered with my friend Jeff Belgic yesterday. When it comes to motors, because of the windings and the polymagnetic wires that they use inside them, and because they're so expensive, they're more expensive than a lot of motors than a lighting fixture like this, right? Air handling units and chillers and so forth. They provide extra, they separate the overload from the short circuit and the ground fault. That's why we stick that electronic overload protection or thermomagnetic overload protection. They separate it because of the importance of the load. What happened to my feeder? I have a panel here, 200 amp fed from 4,000 amp switch gear, right? Where's the overload protection for this panel? The fuse of the circuit breaker will provide. So because it confuses the people, why do the circuit motors need an extra protection? They're important loads and expensive loads. Would the circuit breaker by itself protect the motor? It would, but not fast enough to protect the motor itself. It will protect the conductors, it will protect a lot of stuff, but not fast enough to protect the windings. So that's my so a fault or a short circuit is not an overload condition, as you guys probably have figured that out. Supplemental overcurrent protection device, guys, that's when you go down to they're not branch overcurrent protection device. So I will protect this fixture. So I go put inline 5 amp fuse to protect this fixture. Is that okay? To put inline fuse, buy inline fuse, no problem. So that's your supplement overcurrent protection device. So provide limited overcurrent protection for specific appliances and utilization equipment such as luminaires appliances. All this is in addition to the branch circuit overcurrent protection device that's sitting in the panel. Shall not be used as a substitute. So this is just telling you, just because you put a 5 amp fuse in line with this fixture doesn't mean now you don't need to put a 20 amp circuit breaker at the head of the branch circuit. Electronically actuated fuses. If you use, this is a few things, guys, about the high voltage fuses. If you have, how many of you guys do high voltage? Anybody does high voltage? No? Higher than 600 volt. When you go higher than 600 volt, they have something called electronically actuated fuses. That's smart fuse. So overcurrent protection device have a control modules. It can sense the current and electronically derived time current characteristics, energy initiating tripping, and interrupting module. So smart enough to sense that there's an overcurrent protection condition or a ground fault or a short circuit. The smart is the module. And then it has a mechanism to send the signal to trip the fuse or open the fuse. Initiate tripping mechanism. Electronically actuated fuse may or may not, and they can be current limiting. They are able of being in the current limiting condition. A fuse, a high voltage fuse, guys. A fuse in the high voltage is exactly the same like a fuse in a low voltage. The current pass through a material, it heats it up fast enough based on the size, severe it, open it, and interrupt the current. The smallest, the simplest way of doing it. Heat and severe it by the passage of overcurrent through it. That's any fuse does that. Controlled vented power fuses. What they do is they vent when you have a high voltage, guys, fuse open. Have you ever seen these ones? They have a lot of energy there. So if they're outside, they vent the energy. Controlled vented, they allow the energy to go. So with provision to controlling the discharge circuit interrupting such that no solid material may be exhausted into the surrounding atmosphere. So the energy happens and dissipated inside that fuse. It's controlled. Explosion fuse units.
Vented fuses unit in which the explosion effects of the gases produced by the arc and the lining of the fuse holder, either alone or aided by a spring, extinguishes the arc. So the mechanism, they have a mechanism that a little explosion happen, and part of that one inside it, part of it will extinguish the arc.
When it comes to high voltage, guys, the problem between the high voltage fuse and low voltage fuse is to understand this one, to help me understand it, guys, is by always think of the fuse as not just amps, it's energy. When you have a 600 amp fuse, take the 600 multiplied by 600 volts and 1.73, that's how much energy that fuse can handle. Okay? Now, take a 10 amp fuse, high voltage, and multiply it by 13,800 multiplied by 1.73 and see how much that little amp fuse will interrupt. The amount of energy is huge, so look at it as energy. If you use it as energy, you can see, but if you look at amp, it doesn't mean anything. A 5 amp fuse and 100 amp or 200 amp fuse, yeah, the 200 should be bigger. Well, what's the voltage? So because of that one, guys, there's arcing. Every time you open it, the higher the voltage, the more it's going to arc. So the problem becomes in the high voltage is how we're going to get rid of this arc. So the explosion proof have a mechanism that the explosion that happens inside it will help the arc inside the fuse extinguish or contribute to the extinguishing of the arc.
Non-vented, without intentional provision for escaping of the arc and the gas and so forth. Vented power fuses, okay, I'll get that one. Power fuse units, they can have vented or non-vented, controlled vented fuses. They put all these into a unit. They call it unit fuses. Multiple fuses. They can put fuses in parallel, guys. You can parallel fuses in high voltage and low voltage system. So that's what I'm going to talk. I'm not going to talk too much about the voltage, the high voltage fuses. Any comments, guys? Any questions about the high voltage fuses, the simple things that we did? There's also high voltage circuit breakers. Conductors, other than flexible, you have to have, this will tell you guys that you have to have an overcurrent protection device ahead against overcurrent protection device in accordance with the ambiguity specified in 310.15. So, number 12 conductor, you cannot land on it more than 20 amps, right? With some exceptions for motors and so forth. Protection of conductors, devices rated 800 amp or less. This is probably the single most important one that we do is when we protect conductor from overload. You guys use it all the time. So let's do this one here. So you guys have seen this one over and over probably. Here's an 800 amp panel and or feeder, and I'm feeding a panel right here, and I need to size this one. The up to 800 amp, guys, they allow you to use 2 sets of 500, right? Here's 2 sets of 500 kcm. 2 sets of 500 kcm, 2 sets, not 2 conductors, 2 sets. So if you take the 2, each one of them, here's a 2, multiply by 500 can give you 380, right? From 310.15 B16, and that will get you 760 amps. So long story short, guys, the code say when you size conductors, the overcurrent protection device can be slightly larger than what the conductors are rated for. If it's not, because there is no standard circuit breaker 760, I have to go to 800 amp. If you're using an adjustable circuit breaker, and the adjustable circuit breaker has a setting 760 or lower than 800, you must use that setting. So this applies for non-adjustable circuit breakers. You use as adjustable circuit breakers, you can go the next step, adjustable circuit breaker step. So if I can adjust the 800 down, tweak it down to 770, I have to tweak it down to 770. I can't keep it at 800. Any comments, guys? Any questions? So that's where you can get away with 2 sets of 500 in an 800 amp panel, or 1 set of 500 kcm on a 400 amp panel, when in reality a 400 is more than 380. So how can you get away with it? So that's so protected are not part of a multi-outlet. That's obviously if it's a branch circuit, multi-outlet assembly or plug-in cord does not apply to it, because you don't want to do that one for a cord and plug equipment, because you keep adding to it and you exceeded it. This is meant for feeders, guys, that rule. So the ampacity of the conductor up to 800 amp. Now what happens if I have a 1200 amp panel? 1200 amp panel, you take them, divide them by say 4, give you 300, and you run full amps. So you can't just provide a 1100 amp conductor to feed a 1200 amp panel. You can't do that. Okay, there's limitation on a conductor size, guys, smaller conductor size ampacity. For example, a lot of you guys probably use residential and commercial. So here's a number 14, and we're all talking copper here. If it's on aluminum, is right underneath it. So I have number 14 cannot be protected for more than 15 amps. I want to highlight the 12, and which you guys are all familiar with that, at 20 and the 10, 30. And if you guys think of all your lighting circuits and all your receptacle circuits, right? Think lighting and receptacle. These 3 circuits, these 3 sizes will cover all your lighting circuits and all your receptacle circuits. And in dwelling, these 3 cover 95% of your loads in a dwelling. What's that? Range. That's it. The only see how you can see why they restrict the amps on these, because these are the most commonly used branch circuit in dwellings, and actually the commercial industrial branch circuits, right, for receptacles and for lights. So they want you, because they're mostly common in residential, especially residential, they limit the amount of amps that you put on them. Okay, standard circuit breaker that we use in the US, 15 all the way to 6,000 amps. Anybody have installed a 6,000 amp? Typically 3,000 amp to 4,000 amp is the limit that utility can get you. What happens if you need more than that? Another service. Typically 300. We did 4,000, but 3,000 is preferred by Excel. 3,000 you need more, we'll throw another 3,000 for you. So how many of you guys went to a 3,000 amp service and measured the actual current and you find 3,000 out of it? Did you? So there's a factor that's called the load factor, that after you design everything, you go measure the actual current, and your load factor typically between 30% of your design to 70%. So on a 1,000 amp service, you put your load factor under a rainy day could be 300 amp. Between 300 to 700 amp. If you're pulling a lot, if you have a lot of equipment. So, long story short, we grossly oversized fund, especially at the service, the level of the service. Okay, so this is a few things, guys. We talked about spaces. The reason why we bring spaces around electrical equipment working, how is this related to the overcurrent protection device? What does the overcurrent protection device provide protection from? Protection from arc, right? So arc flash. What's enemy number 1 of arc flash? Being trapped, right? Why do we have the workspace? Not only to work, this is workspace for working energized. Working de-energized, the workspace is supposed to be for working energized. If you're working de-energized, it's as small as you feel comfortable. You mean? But these are working energized or testing equipment or living circuit breakers. So the width of the equipment, the height 6.5 feet, that's base to the width of the equipment, or 30 inches,
to a height of 6.5 or the height of the equipment to the depth of between 3 feet to 4 feet, depending on the voltage and the condition. These are sacred area. This is to allow you to get the hell out of there if there's a big arc, flash, big ball of fire chasing you. Right? So that's, and you're not trapped. You're not trapped.
Okay. Overcome protection device. A couple of things, guys, when it comes to the overcome protection device too, that we deal with. Supervised industrial installation. If you have supervised industrial installation, they allow you to do a lot of things that we normally don't do in a commercial building. But look at the condition though. You have to have your very qualified service people working on it. Here's the 25 kVA, 2500 kVA or greater of industrial process and manufacturing. So they're really restricting it, right? And supplied by at least a service more than 150 and more. So at least have a service of 480 to 77, right? So not 208, at least one service. If you have a 480 277 building and the service, the manufacturing floor is consuming 25, that's 2.5 megavolt amp. That's a lot of power. And qualified people maintaining it, you can do anything you want, almost. They relax the overcome protection device requirement. You're going to see you can do a lot of stuff because, you know, if you can size tab rules become relaxed. This is not open to the public. You know, they have smart people maintaining it, so they relax the rules a little bit for places like this. We talked about ground fault protection for equipment, guys, and I mentioned that required for 1000 amp and any voltage to ground higher than 150, that will get you what? 480 277. You shall not, it's not required on the following industrial process. So you're cooking chemicals. Do you want to put a ground fault? So if you trip, you know, you create more hazard by interrupting the process? No. How about your fire pump, that pumping fire? Do you really want to, as you call on the fire pump to come in, oops, we have a ground fault, we're going to trip, we'll wait. You can see that. And installation where GFCI protection required for other requirement for the service provided by other requirement. This is when the GFCI is part of the circuit breaker, so you don't need a separate GFCI. If you have a GFCI part of the circuit breaker, ground fault protection part of the circuit breaker, which is all circuit breakers at certain value, they have them, then you don't have a separate relay that can trip a disconnect. You know, if you don't have a circuit breaker, the way they do it on fuses, they have a separate relay that trip the switch. If you have a circuit breaker, you have built-in sensing mechanism that can look at the phases and the neutral and analyze it and come up with a value to trip at the ground fault. Okay, shall be connected. This is just telling you guys, if you have an ungrounded conductor, you have to have a circuit breaker right ahead of the point where you feed these in series with them. Ungrounded conductor, the circuit both manually. So the circuit breaker as overcome protection device, circuit shall open all the ungrounded conductor. So not only the circuit breaker is going to act as your disconnect here, but also it's going to act as the overcome protection device for these conductors. This is a few things about, guys, about ungrounded conductor multi-wire branch circuits. Long story short, when can you use a single pole circuit breaker to feed a 3-pole load with a tied approved handle? So if you have a single phase circuit breakers, you tie them with an approved handle and you can take them, feed multi-wire branch circuit 277 or 120, no problem. If you have a 2-pole circuit breakers, you tie them with an approved handle and you can make them feed 240 loads. Like a chiller, not a chiller, in a house, what do we use in a house? And air conditioning and so forth, that's approved. You can go as high as 208-120, 208 3-pole tied together with a grooved handle to feed a 3-phase 208 system. That's okay. The only time you cannot do is to feed 480 system, 2-pole or 3-pole. So if you have a 480 system, 2-pole or 2 hots or 3 hots loads, you have to have a 3-pole circuit breaker. So that's what these requirement is telling you. And of course, if you have a multi-wire branch circuit, you have to, as we all know, if you if these lights here are fed from 3 different circuits, each one of them is 277. Let's just say it. They're fed from 3 single-pole circuit breaker and sharing a neutral. That's called a multi-wire branch circuit. So you have to tie the 3 circuit breakers together with an approved handle. With an approved handle. With an approved handle. I'm going to give you guys a break and listen a second here. Just hold your horses here. Line to line. The line to line load that you can feed, guys, like I said, 240 line to line, single phase, no problem. 208 line to line to line, 3-phase or single phase, no problem. You cannot feed 480 3-phase loads out of 2 or 3 single pole circuit breakers. As we all know, guys, if you have a multi-wire branch circuit, they have to be identified. That came in 2008. Can you guys see how they group? They have to be grouped together, tied together, unless identification is clear. If you guys are there, would you be in doubt that this neutral is shared between these 2 hots? It's very clear. So you don't have to wrap them together. But the top here, you have to wrap the 3 hots or the 2 hots with the neutral. You know why? Because they get confused now. You know, if you want to work with them, you get confused. You might use neutral one with phase A and phase A. So you overlap them. And of course, they have to be tied. So these have to be the circuit breakers here, as you can see, tied together. A circuit breaker is tied together, and a circuit breaker is here tied together with an approved handle. Any comments, guys? Any questions? Any comments? Any questions? Did I put you to sleep yet? No? Working hard on that? Okay. So that's, you know what? This is a good time to stretch yourself. Go stretch your feet a little bit. That's a good breaking point.
Make big air conditioner units, units.
Yeah.
And they have test stands where they, have a big test stand with wires going to it so the operators can test the whole unit.
Okay.
One of the new guys used an impact and loosened up all the lugs before he disconnected power.
Oh my God.
Pulled them out and it hit the shell, the sheet
It
metal of
arcs.
the unit.
Yeah.
400 amps. And well, it blew one of the 400 amp fuses at the test stand, and then it went through the bus duct, and we had this old open bus duct which was vented, and just at one random point it just blew up and sparked all over the place, and ended up blowing 2 of the 1,000 amp fuses at the main switch. And I can't imagine if that was only a quarter of a cycle, what anything longer than that would have just been worse.
Oh my God. Wow.
Yeah.
That's interesting. Oh my God.
Been replaced since then.
I tell you, wow. It does a lot. If you look at where you look right here, it gives you a lot of stuff. It gives
You want to look up, say, arc fault. So you arc fault.
well, I use it for arc fault between the two.
So here's circuit formulas and voltage drop calculation. So it does that. Conduit cables and underground installation, and basically and box code calculation. Here's the sizing of word and boxes. I can't recall that I've seen that.
It probably doesn't, I was just using it.
Yeah, grounding and bonding. Maybe I just can't recall seeing it because I just don't look for it here. Motors, a lot tons of information about motor size, like you just did with just transformers, communication and electronic equipment, electrical job safety and materials and tools, and then the conversion factor symbols and terms. Yeah, I can't recall. You can check. Okay.
takes you almost a week. So the home run, an hour and a half, right? I was thinking of the 60. I would if I was not, if I could do it better.
Yeah.
I didn't tell you what I was planning. I was that close to canceling the class or not showing up. Just that antibiotic is bothering my tummy. But we will pull it though. I don't like to cancel class. I never did cancel class. I know how important it is for you guys. And it's fine to have. Yeah.
Especially since we moved around, this is the last class before our license.
Is it, when have you guys were doing journeyman's? Yeah, because masters was just passed.
They were all, I think they did all the masters ones like February.
Yeah, that's where. So June, you guys are June, yeah. Okay. See what? The timing is different. Yeah, I think all the mass are February 28th. Yeah.
Is that what it is? No, it's
Where? I can't remember. I know mine anyway. I think I don't know way ahead of time, so I can never. Never pay attention. Yeah. So effective date, expiration date 02/28/15. Yeah, every February 28th.
So if you guys come across one of these books, make sure you wait. I like them. What is about when? Huh?
How hard was that one to find?
Well, I have a collection up to the 40s, full collection. Up to the 70s, it was easy. Anything from the 70 up, very easy to find for nothing almost. But you hit the 60s and the 50s, you start paying $82. I think something like this, probably looking at, I paid for it 10 years ago, $100 almost, on average. Yeah. I think now probably looking at $120. eBay. I got them all on eBay. So there's one 1918. 1918 mint copy. Went for $1,800. I was willing, and I'm not rich, I was willing to pay $600 for it. But I always feel I left it after that because my wife will divorce me after 600. So I stopped bidding on it and kept watching. It went for $1,800. I mean, what is an $1,800 for a big contractor who makes a lot of money to put it in his office? When you think about the scheme of things, bragging rights, like this is that big moose that you shoot over here.
The other thing is to memorize it really easy too.
Yes, small, right?
Okay, so let's go ahead, guys, and reconvene. We have an hour and a half. An hour and a half to do a few things here. Let's go about the disclaimer, telling you what I'm going to do, guys, for the an hour and a half. Hopefully, we'll go over temperature device location and installation, the cab rules. We'll touch the cab rules. I know yesterday you guys with Jeff Kiljick, I assume you guys sized the overcap detection device for motors, right? Very easy. There are you either 300 or 175 or 250 or 800, 4 ways, right? You size the overcap detection device. I'm going to tell you as an engineer, when you size the overcap detection device in real life for dual element, if you use dual M time delay fuse or inverse type circuit breaker, these two, you can literally size them based for motors. You can size them 1.25, not 2.5, 1.25, and go up, and you're almost there 95% of the time. So why do we care, guys, about sizing them less than what the code says for? The lower you size the overcap detection device, the less the arc flash that is going to happen if you were to have an arc flash condition
inside your motor controller.
So, so let's talk about the tab rules, guys, the overcome protection device. Overcome protection device, guys, provide, you must put the overcome protection device ahead of the conductor. So when you size, and this is not true in all the condition, here's my overcome protection device inside the panel. When I want to size my conductors, you're going to go, let me see if I can get the yellow, if it works here. So here's my conductor. This is where you can bowl your conductor, right in here, and you tie it to your equipment, right? Here's my conductor. So ahead of the conductor. That's the rule. Now let's go to the exception. The exception is you can have your overcome protection device at the bottom of your conductor instead of ahead of the conductor to protect it. So that's called the tab rules. The tab rules. So a couple of tab rules, guys, you're going to see. So I have an overcome protection device over here. I can tab this overcome protection device, go down here 8 feet or 10 feet, and put an overcome protection device and tab. So here's my conductor that I tabbed here. Where's the overcome protection device that protects it? None. Non-existence. These are the exceptions. So the rule, fuse or circuit breaker ahead of the branch circuit or feeder, or feeders and branch circuit, then the conductors to protect you from over current protection condition. Tab rules. I want to summarize this tab rule, guys. This is tab rule number 10. 10 feet. Tab rule 10 feet. 10 feet tab rule, guys, is really very easy, very simple when you use it. It helps you a lot if you are a contractor, you want to save money. So which a lot of you guys are, and you want to save money. So I have an overcome protection device right here, a feeder, and my feeder is 400 amp, right? Let's just say I pulled the 400 amp feeder, and I put that feeder into a gutter, right here, and this is inside a disconnect or a panel, and I tab from here, go 10 feet, put an overcome protection device or a circuit fuse, and feed here's my disconnect fuse or circuit breaker, and feed a pump or something. As long as you don't go further than 10 feet, from here to here is 10 feet. That's your 10 feet rule. Okay, so the rule for the 10 feet, guys. So the rule for the 10 feet, you can't go more than 10 feet, right? Tab, 10-foot tab. Number 2 is you have to land the conductor in an overcome protection device. Can you guys see that? So if the conductor is rated for 100 amp, you have to put a 100 amp circuit breaker to limit the current to 100 amp. Very simple. You have to put it in a conduit to protect it from physical damage. And the size of the conductor is the minimum size. The maximum size is the sky. The minimum size is 1/10 of the overcome protection device. So here's my main is 400. Divide the main by 110. Gentlemen, that will give me what? If you divide it by 110, that'll get you 40, right? 40. Here's my 40 amps. So what size conductor, the minimum conductor that I can pull out of a 400 amp? 40 amp. Okay, 40 amp conductors. Let's say the lugs here are rated, let's just say the lugs here are rated for 75 because everything is 3-phase. Everything is rated, and my conductors are THHN. Would that be number 10 or number 8? Can you guys go to table 310.15b16? I think I can't remember if number 6 will cut it. Can anybody? So 40 amp under 75. Is it number 8 or number 6? I can't remember. Number 8? Okay. So number 10 cannot cut it at that value. So the smallest conductor that you can tab is number 8. The smallest conductor that you can tab is number 8. Now, what size overcome protection device do you need to protect it? Number 8 is right here, 40 amps. So you put a 40 amp circuit breaker fuse at the bottom of this cable, and then you pull a number 8, and that section, the 10 feet, is protected from short circuit by the main right here, and from And from overload, what's going to protect it from overload? Do you think a 400 amp circuit breaker will protect number 8 from overload? No way. So what's going to protect it from being overload is the 40 amp at the end. So these are the rules for the 10-foot tab rules. You can't go more than 10 feet. You have to protect them from physical damage. Typically, you put them in a conduit. For field installation, that's what we do. You have the conductor cannot be less than 1/10 of the overconduction device. 400, 1/10 of 440. That will get you number 8. Any comments, guys? Any questions about the 10-foot rule? Any comments? Any questions about the 10-foot rule? Really straightforward. Take advantage of it. So now let's say. Now can I put number 2, number 3, number 4? Yeah, no problem. So you can go take another feeder here. Let's just say another feeder here. Write the same thing. Here's my disconnect. Here's my fuse this time, and I have my disconnect here. I'm going to feed another machine out of it, or another little load out of it. And let's just say that I'm going to use number 1. Can you guys? Does number 1? How much current number 1 can carry? Is it 130? So that can be 125. 125. So I have 125 amp fuse. Remember, everything is rated for 75. The lugs are rated for 75 on both ends. 3-phase systems. So I have number 1 feeding 125 amp fuse that feed a machine. That machine, you guys were sizing with my friend Jeff Keljic here yesterday. So you can see what size the overconduction device of that machine cannot be more than 125. That's the only condition that you have. As long as you can meet that condition, the tab rule is good to go. Any comments, guys, about the 10-foot rule? Let's do the 25-foot rule. The 25-foot rule, let me go get a different color. That's a good one. Here's a color. I hope none of you is colorblind, I can admit here. Doesn't make... I had the low voltage technician colorblind. How can you be a low voltage technician and colorblind? With all the respect, I mean, just all the wires that like low voltage wires. He's a friend of mine, and he figured them out. I don't know how you can figure them out. Like, you know, the phone wires, these all twisted pairs and Cat5. I'm not colorblind, and I can't figure them out. They're so close in color anyway. Okay, here's another feed. Now we're going to go all the way down, guys, to 225. Here's my disconnect. Here's my fuse here. I'm going to go all the way my machine. This one is a 25 feet tap. No more. Everybody knows when we say 25, no more than 25. What's the size of the conductor that I can tab no more than 25 feet? The rules are the same. The conductors that you tab have to be terminated at a fuse or a circuit breaker or a set of fuses or circuit breakers that limit the current to the minimum, to the maximum current that the conductor can carry under these circumstances. So let's go find the conductor. And you have to put in a conduit to protect it from physical damage. And the rule number 3, the most important, the conductor size cannot be less than 1/3 excuse me, of the overconduction device, which is 400. What's 1/3 of 400? 333? 333, right? Would that be 500 kcm? 333 under 75-degree column. What size would that be? I'm sorry, 100. 133, not 2. My apology, 100. You're right. Why 33? 100. 133, how much? 1 aught. So I have 1 aught. The minimum conductor size up to 25 feet that you can go with inside a conduit, EMT, rigid, PVC, to protect it from physical damage, is 1 aught. The next question would be, how much 1 aught can carry, amp-wise? So 1/0 can carry 150 amp, right? So what's the conductor? What's the fuse? The maximum fuse you can put here. 150. Right? Because 1/0 cannot carry more than limited to 150. Then my fuse is 150. If 150 wasn't the standard fuse, what do? You go down. So I have 1/0 landing on 150 fuse. The fuse is the most important thing. The overconduction, not the disconnect. The fuse. Then I can go size my load there and see what. As long as I maintain these, I'm good to go. Any comments, guys, about the 25 feet tab rule? Tab rule for 25 feet. Does it make sense? No? Yes? 25 feet. So from the same feeder, now can I keep doing it, Chad, for an unlimited amount of loads? Keep in mind, the more loads you add, the more you might exceed the capability of the 400 to do it. So you have to do load calculation to see if 400 can handle it. How do you do a load calculation to see if 400 can handle it? You take the largest motor among all these equipments, right? Multiply by 1.25. Add the full load current like you guys did with Kildrick yesterday to it, and make sure that the feeder here. So let's say that let's say just sizing it here, I'm sizing 500 kcm. That's a feeder that I'm tapping. kcm. Then kcm, right? Then you have to go size 1.25 times the largest plus everything else. Make sure you don't oversize. You overload the conductor that you're tapping. Huh? Or, yeah, you're so right. Or you can trip the circuit breaker. Right? Overloading it meaning trip the circuit breaker. That's a bad design. You can trip the circuit breaker to overload it. Yeah. Okay, so these are the rules of the tab rules, guys. Let me see if we got that one. So this is the 10 foot. Here's the 25 feet. 10 and 25 feet, the rules, the tab rules. You can see how you put the gutter here. Great opportunity to tab and feed multiple conductors. Makes sense? Tab. And it doesn't matter if you tab with a foot or with 2 feet. It's you tab with less than a 10, you apply the 10 rule. You tab more than 10, you apply the up to 25, you apply the 25. Can I tab more than 25? Not inside the building. Not inside the building. You'll see where you can tab more than 25, not inside the building. Okay, so here's my tab rules, guys, 25 feet. See how we tab them. You have to land them at the end with an overcome detection device, as you can see. Now tabbing tabbing the primary and the secondary of the transformer, guys. When you tab in the secondary of the transformer, we have a couple of rules. When we talk about the transformer, we're going to go over them in less than a second. So here's the rule. So each set of conductor feeding a single load, so you shall not be permitted to. So when you tap these, look at these. They have to land with an overcome detection device in each one of them from the transformer. But these conductors here shall not exceed, depending on what rule you use. Is it 25 feet or 10 feet? Primary and secondary shall not exceed the overcome detection device here multiplied by the ratio of the voltages. You'll see in a second how they do them. Transformer secondary conductors. So conductors supplied by secondary side of a transformers, blah blah, shall be permitted to be protected by overcome detection device on the primary side, provided the protection is according to 450.3 and does not exceed the value determined by multiplying the secondary conductor ambiguity by the secondary to primary transformer voltage ratio. So so we have where is that one here? Chat. So we have a transformer, guys, and here's my transformer coming in here. Here's my primary and secondary, and see it's a 10-foot primary and secondary from right here. Say the 10-foot. Really, what the protection should be in the 10 feet is right here. 10 feet the secondary, because the primary is already protected here. So the 10 feet the secondary. The way they do them, guys, is take the, and this is, of course, have to land on a circuit breaker. Must land on a circuit breaker. And there's a circuit breaker right here, right? 10 feet. So what you need to do is same thing. You have to put them in a conduit. You have to protect them. Blah blah blah. What size conductor do I need right in here, though? What's the minimum size conductor? So let's just pick. Let's put 100 amp here, right? Let's say we size the conductor as 100 amp here. If the overcome protection device was 100 in this side, what's the minimum conductor on this side that I can use? Let's use a voltage. I'm going to use it to make it easy, and I'm using 480 here, and on this side 240, just for the sake of the ease calculation. So the ratio is 2 to 1, right? So that conductor here, guys, here's how they calculate it. You have to take same thing, 110. Here's my 110. Multiplied by the rating of the overcome protection device. What's the rating? 100. Now, because it's on the primary side of a transformer, you have to take into consideration the voltage ratio, right? So any current on the secondary will be seen on the primary half of the same amount, a half. 1 amp on the secondary will be seen as an amp, half an amp on the primary. So you multiply it by the voltage ratio, basically. What's the voltage ratio? 240, 24 divided by 480. It has to be 240 divided by 480, not the other way around, because the amps on the secondary are going to be seen on the primary side as half, right? Half the ratio. Okay, so do this. So if you guys do the math on this, so 110, that will get you 100 divided by 10 is 10, divided by 2 is what? Is that 50? Divided by 10 though, 5 amp. So this is the smallest conductor that you can put, the smallest conductor that you can put on the, did they do the math right? 100? 240 divided by 480 is what? Yeah, because we're gonna multiply by the secondary. You have to take the voltage ratio. 25, 50 divided by 2, 25. That's more like it. Yeah. No, 100 divided by 10. No, right. Yeah. Yeah. Yep. Divide by 10. 5. The minimum conductor that you can tab there is 5. I know it's ridiculous, amp, but just will give you an idea. The minimum conductor that you can tab out of this transformer for 10 feet is 5. So obviously we don't put a 5 amp conductor. The minimum they put is number 12. Because the current, this 100 here on the primary side, when you move it to the secondary, it will be seen as half, right? Because of the voltage ratio. Or you okay, so you're going to multiply it by on both sides. You're right. I think this should be the other way around, because when you move it around, this should be 480, because we're moving it to this side, not the other way around. So this should be 480 divided by 240. Okay, so that will give me what? 10. That's about right. Okay, you're absolutely right, because we're moving it, it's here, and we're applying it here, so we have to cut it by multiply by 2. So I'll give you 10 amps. Oh, yeah, the 20 amps, thank you. 20 amps. Keep doing it. 20 amps. Did I confuse you enough, huh? 20 amps. Because you take the voltage on the primary side, move it to the secondary, it doubles itself. I was just looking at it differently.
Make sure you don't edit that out of the video.
Well, it's all the mistakes are already there. You can see them. Is it, everybody's the brain is okay, 20 amps. So what conductor size would be then? Number 12. Number 12. The minimum that you can size. Number 12. So that's the conductor, tabbing the conductor on the secondary side. Transformer. You cannot round up. That's also on the oops. That's also, guys, on the test. You can't round up on the secondary side. For example, very, very important. If the size of this panel, this circuit breaker, because of the tab rule, if the circuit breaker was 100 amp, can this feeder, can this feeder, went all the way out, can this feeder be 95? Right? Like that round up rule up to 800 does not apply here. They like to test people on the master and journeyman with it. That rule of rounding up does not apply when you tap. So what does that mean? Meaning your feeder have to match your overcomputation device here. Or be bigger. Does that make sense, guys? Cannot use the 240.4b to round up. So secondary conductor is 10 feet, the ampacity not less, overcomputation device, not less than the rating of the overcomputation device terminated on the equipment. That's what we just went through. Disconnect secondary conductors, sending, and for field installation, here's where that we got confused. The rating of the overcomputation device, right in here. Protecting the primary of the transformer multiplied by the primary to the secondary voltage shall not exceed 10 times the ampacity of the conductor. We were applying a reverse function. Instead of taking the ampacity and sizing the circuit breaker, we found the circuit breaker and we see what the minimum conductor that you can size. Any comments, guys? Any questions about that one? Any comments? Any questions? So that's my conductor secondary transformers. We talked about that, and we take advantage of this one all the time, guys, when we size the receptacle panel. That's how you get away without putting a fuse right in here, right? Otherwise, we have to put a fuse right in here at the source of the fuse disconnect, right at the source. Transformer secondary conductors, 25 feet. The same requirement, guys. Transformer secondary conductor 25 feet. Overcomputation device and the sum of the overcomputation device does not exceed the secondary conductor ampacity. When you land them, the sum of the overcomputation device does not exceed the secondary conductor. But for field installation, you use the 1/3. For field installation, you can use the 1/3 overcomputation. Where does it say that? Secondary conductor protected from overload for the transformers, 25 feet. Okay, shall not be 10 times with the secondary. Okay, we got that one. So for the 25 feet, let's do that one on the 25 feet, the one that we just did. Okay, so suppose that this transformer was 25 feet, so you're going to come over here. So this time we're going to do it right? From the so here's my 25 feet and a overcomputation device. Give me an amp. What did we start with? 100 here? Shall we do 100, the same thing, 100 amp here, just for the sake of that? and I have a 25 feet secondary conductor from here to here. 25. Cool. So the same thing, guys. You're going to do, the rules are to size it. This conductor is going to be, let's start with 1/3 this time. 1/3 multiplied by the overcomputation device, which is 100. Our voltage is same thing, 480. 2.8 on this side. Shall we do 2.8? Anybody has a calculator? Well, let's do 240 just to see, compare what we did. So that will be multiplied by 480 divided by 2.8, Chad, not the other way around. Okay, how's any math? Anybody can give me the math, please? So what's 50, right? So this will be 200, right? 200 divided by 3 is what? What's 200 divided by 3? How much? 66. 200 divided by 3. 66. Right? So 480 divided by 240 is 2. 2 times 100 is 200. 200 divided by 3 is 66. 3, 1/3. Oh, you mean 33 times 2. I see what you mean. Yeah, you're right. This is not working at the end of the day. You're right. 1/3 of 100 is 33 times 2 is 66, Chad. Okay, so what size conductor? Can you guys find a conductor under 75? That would be number 8, more than number 8. Number 4? That would be your number 4. Number 4 conductor, under 75-degree column. Okay, how much current number 4 can carry, guys? Under normal operating condition, 75. How much? 85. Okay, then you can go up to 85, so this cannot be more than what? 80. So that circuit breaker cannot be more than 80 amps. To limit the voltage to the capability of that conductor. Any comments, guys, about the tab rules? Any comments about the tab rules? They're ugly and icky, sticky a little bit. But really, the difference 25 and 10, the only difference when you have a transformer is just use the voltage. You use the voltage to transfer the amps from one side to another. Transfer the amp from one side to another. Okay, so we transformer secondary conductors outside. Now inside the building, everything that you've seen is inside the building. Now what happened if I want to tab a conductor outside the building? The limit is the sky. Who cares? Remember that the National Tech Code is written by firefighters, guys. If you have fire outside, up in the air, it's not as dangerous to the building as if it's inside. So really, the rules relax when you go outside the building. You're not burning building. You're not trapping people in the burning building, right? So if you go outside, you can. The only decisive factor becomes is you have to pay attention to really is short circuit. You can tab any conductor from any conductor outside as long as the overcome protection device can protect that conductor from short circuit. Number one. And the conductor is protected from overload by a fuse or a circuit breaker. So then you can tab and go as far as you want. No limitation on the distance. No limitation on the distance if you're outdoor. So the conductor is protected from physical damage, terminated a single circuit breaker. The disconnect means for conductor is installed at the readily accessible location outside the building. But it doesn't talk anything about limitation. You have to protect the conductors, everything, because of short circuit and ground fault and so forth. But no limitation on how far you can tab. No 10 foot, no 30 feet, whatever. Because we're outside the building. Okay. Talk about that one. The conductor shall not be 10. Okay, we talked about that. This is just a couple of things, guys, about the battery overcome protection device, as long as we're on it. Permitted to be installed as close as practical to the storage batteries, but not in the hazardous location. Let me go, as long as we're on it, let me just go to the tab rules, guys, just for a second. I'm going to highlight, okay, here, tab rules, 240. There's a few tab rules, guys, that, okay, so here's small conductor. We talked about the small conductor, all this good stuff. 240.21, I believe, would start. Okay, here's the rules, guys. You have your book with you. It all start at right here. Here's the tab conductor. Basically, 240.21. The 10-foot rule that we talked about, you guys, we've done it here. That B for feeder number 1 is the 10-foot. Number 2 is the 25. Tab supplying a transformer, primary plus secondary. This is also, guys, the tab supplying a transformer, primary plus secondary. There's also, you can tab to supply a transformer, 25 feet. We did not do that one. If you tab primary plus secondary, not over 25 feet, look at that. The conductor supplying the primary of the transformer have an ambiguity not less than 1/3 the rating of the overcome protection device protecting the feeder conductor. The conductor supplying the transformer cannot be less than 1/3. The same thing, except now they divided, the 25 feet is 1/3, but they just divided the distance between the primary and the secondary. So, and the conductor supplying the secondary conductors not less than the primary to the secondary ratio of 1/3. So, so that's where really interesting. So, when you have the primary and the secondary 25. So first of all, the primary conductors cannot be less than 1/3 of the feeder, and second, the secondary conductors cannot be less than 1/3 of the feeder multiplied by the voltage ratio. Does that make sense? When you have a transformer and you tab a feeder to feed a transformer, So the examples I did, the primary were not tapped. The primary conductors were not tapped. Your primary conductors were not tapped. So that's why you can, that's my favorite, the 25, because if you have a transformer this way, here's my transformer, and 25 feet, or 10 feet, the same way, guys, from here, and my overcome protection device is right here, and the distance from here to the overcome protection device right here is 25 feet. That's what they're talking about, the whole distance, 25 feet. Look how interesting when you do that, this becomes 25 feet. Let's use a 300 amp here, just to make the calculation, 300 amp fuse. Okay, so the 300 amp, then the conductor size here cannot be less than what? 1/3 of this. 1/3 times 300 give me what? 100. Can you guys give me a size of 100 amp based on 75, 100 amp? Is it number 1? Number 3. And that will be a conductor size number 3. Cool? No question asked here, number 3. Now you go on the secondary side to size your conductor here. Piece of cake. You're going to do the same calculation, that, guys. 1/3 multiplied by the 300, except what do you need to do with the voltage? Let's use the voltage 480. Let's do a realistic one, 480 208. I need somebody to do the math on that for me, will you? Because now it's complicated. Multiplied by 480 divided by 208. 480 divided by 208. How much? All of them, the whole thing. So 208. So that would be the size of your conductor. Don't we use this all the time, guys? that rule at 25 to go for the receptacle panel, what did you get? 231. 231 amp. Now, what's the size of conductor? That will get me a 2-aught or 3-aught? 3-aught? I think 3-aught can give me 225. That must be 3-aught, right? So that size will be 3-aught here. And what size overcome protection device can I use here? You guys got 3-aught? How much? 225? 225. 250. Then you can go as high. Yeah, you go by the conductor size. The largest that you can put here is 250. You don't have to go 250. The largest that you can go is 250 or less, because you go by the size of the conductor. What is it, 4-aught or 3-aught?
3-aught. 3-aught is good for 200. 4-aught is good for 230.
Then this is 4-aught. And what's 4-aught good for? 230. Then this will shoot 225. I thought you guys are helping me. Okay, right? Are we good now? So 4-aught, I'll give you 225. Any comments that make sense? The calculation? So that's your 25 feet primary and secondary. Primary and secondary. Can you use a 10-foot primary and secondary the same way? Yes. The only difference when you do a 10-foot, guys, is you divide by what? 1/10. Primary and secondary. Secondary. Watching the time here. Okay, so let me. So that's this rule, guys. At 25, tab over 25. Over 25, guys, where the feeder is in a manufacturing building, you can go up to 35 high walls and blah, blah, blah. Maintenance and condition, smart people maintaining it. You can go even higher than that. Up to 25 long horizontal and 100 feet vertical in the manufacturing. Not less than 1/3. See how it's special for manufacturing. You can go up to 100 feet total. I'm sorry, 100 feet total. 25 feet long horizontal and not over 100 feet vertical, all total. So that's special for manufacturing. You can see there's a couple of other rules. Outside unlimited length. Bring it on. You know, as long as you protect these conductors from the being overload and from short circuit. So that's a couple of things, guys, about transformers. Same thing outside, transformers outside, you can protect them. No limitation on them. These are the conductors. So that's basically the rules, the most important things about the rules of the tab rules. Next year, guys, or 2 years from now when you come, my plan is to draw all the stuff that we did for all these, draw them really nice, and do a couple of examples like I did with these, because they confuse me as much as they confuse you. They have to read them over and over and put them, and we'll be putting them on YouTube. So that's kind of the plan. Okay, so that's the rules of the, a couple of rules of tab. The reason why we picked the tab rules, guys, because they're the most complicated things for the overcomplication device. Really. You guys did the motors yesterday. Other than motors, when you start the overcomplication device, is it continuous load? Yeah, multiply by 1.25 and go out. Done. Really. Is it non-continuous load? Then multiply by 100%, and go up if it's not standard. Conductor-wise, the same thing, guys. Make sure your conductor is 1.25, go to next standard. The only you start watching what you're doing when you hit the 800 amp. You have a panel 800 amp. Your conductors can be lower amp-wise, slightly lower. More than 800 amp, match the conductor to the overcomplication device. on panels. Okay. Overconduction devices, guys, have to be readily accessible with some exceptions. And for short people like your friend Chad, they have to be 6'7" because we can't reach them. The top operating handle cannot be more than 6'7". Must be snuck by a short guy. That one. For busways, for supplementary overconduction device, and for utilization equipment that they supply, access shall be permitted by a portable means. So there's a couple of exceptions, guys. Like for the busways, you can have it higher than that as long as you have a handle that you can grab it and turn it on and off with it, a stick or something. Supplemental overconduction device, if you have a fuse over there, it doesn't have to be, or circuit breaker, supplement inline fuse. Doesn't have to be within sight of the, readily accessible. So these are a few exceptions for the readily accessible location. Equipment, as long as it's right next to the equipment, and you have a means of putting a ladder or something to reach the equipment, because the disconnect have to be within sight of the equipment, right? And most likely the equipment is going to have a fuse to protect the equipment, so that's okay as long as as long as you have access to the equipment. Occupancy, service and overconduction devices shall have. So this talks about, guys, giving access to the overconduction devices in occupancies for people who are residing there, with some exception, to be accessible only to shall be permitted to be accessible only to authorized management personnel in the following: multiple occupancy buildings and guest rooms or guest suites. Guest rooms and guest suites, they allow you to put the panels and overconduction device somewhere else. Apartments, you have to give them access to their overconduction devices. Building under continuous operation management. So, and this is just talk about if it doesn't have cooking, shall be permitted to be accessible only to qualified people for guest suites and guest rooms and so forth. Not exposed to physical damage. You don't want your fuse or circuit breaker to be exposed to physical damage. You don't want to put it in a class 1 div 1 location, obviously, unless it's rated for a class 1 div 1 location. Closed closet, you go stick a fuse or a circuit breaker in a closed closet. That's ignitable material. You don't want to do that one. Not located in bathrooms. You can't put overconduction devices, fused or circuit breakers in bathrooms of guest rooms or guest suites or hotels and motels and dwellings and so forth. Not located over steps. I'm sure somebody tripped and break their neck, and they added this one in 2008, if you guys remember. You can't put them over steps now. So you can put it over a landing, but not over the steps. Did it bother you guys when you... No? Okay. A couple of things, guys. You have, like, overconduction device reside in something called panels, and panels have to have a directory that identify all the equipments and the location controlled by the overconduction devices, including the spare ones. Operating handle of the circuit breaker shall be permitted to be accessible without opening the door or the cover, as we all know when you go to the panel. Vertical position. When you put the circuit breakers, overconduction device shall be mounted in a vertical position unless that is shown to be impractical. Enclosures have to be in a vertical position. Meaning, can I grab the panel and set it instead of upside down, sideways? I heard that they do it in Canada to fit. Somebody told me in one of my classes. They do them sideways, they flip the panel. So you're not supposed to, unless it's impractical. How are you going to come impractical? That's kind of the words that, yes?
We have a situation where we're trying to change out the panel, and it's got like a cinder block wall this high. The panel won't fit anymore.
So
Instead of building a wall, we haven't addressed it yet.
here you go, impractical. Grab 240.33. Yeah. and talk to the inspector. Say impractical. Yeah. What we did now that design wise for certain customers, guys, if the switch gear is high enough for the room, there was a situation in Mayo Clinic for like this. A friend of mine was involved in it. Then you involved somebody like EMI, electromechanical industry, and they custom design a shorter than normal switch gear for you, and you can fit it up to 5 feet, and they make them bigger this way instead of higher. So, and it meets your listing, but that's designed by manufacturer though. But that's your refuge, my friend. Disconnect means for fuses. This talks, guys, about cartridge fuses. Cartridge fuses in circuits of any voltage were accessible to other than qualified person, and all fuses in circuits over 150 to ground, that's 480 and 600 to ground, shall be provided with a disconnect means on their supply side, so that each circuit containing a fuse can be independently disconnected from the source of the power. So you have 480, 277, you have to provide a disconnect so you can disconnect the circuit before you access the fuses. Fuses shall be located so that the person will not be burned or otherwise injured by their operation. So that's the orientation of a circuit breaker. I guess the good example of this, a bigger circuit breaker, when they trip sideways, not right on somebody's head. This is a couple of things, guys, about fuses. And so we have classification of fuses. The plug fuse up to 120, as I don't know how often we don't use it in homes anymore, but that's probably for protecting machines that you can use. Anybody using 120 to protect machines up to 30 amps? Replacement only. Plug fuses of Edison shall be used only for replacement. Why? Because people tamper with them and overfuse. This is just a couple of information about different type of plug fuses. Pennies, so you can stick them in there, and they will not trip at all. Shall be installed only where they are made to accept, and they have the type S fuses, guys, by the use of adapters. So it limits you, since they're 30 amps, it prohibits you from putting a 20 amp where a 15 amp conductor has been terminated. Plug fuses with the adapters. So then we talk about the classification of the type S fuse, guys. 120 take you can see that the intention here is to prohibit you from putting a 30 amp on a number 14 conductor. Can you guys see that? So you're talking about these limits are really this. You talk about 14 wire gauge 14 here. This is gauge number 12, and this is gauge what? Number 10. So very clearly why they labeled them in that range. It goes nicely with the most common brand circuit conductor that we use. And they say the types shall not be interchanged, where you can put one 30 amp can be installed in a place where you should put number 15. Maximum voltage. So this is a few things about the fuses. 300 volt type. Hold 300 volt up to 300 volt. That will cover 240. 208 type shall be permitted to be used in the following: to feed single phase line to neutral, and for 3-phase 4-wire solidly grounded neutral wire. So you can see where they limit you with these type of the 300 volts. So your single phase or 3-phase solidly grounded equipment. Non-interchangeable. They want you to design, guys, when they design the fuses, they design them in a way where a higher amp fuse cannot be placed in a lower amp fuse holder. So that's the most important thing amp-wise. Or you do not want to put a higher voltage fuse in a lower voltage area too. So voltage and amp have to match, the maximum voltage and amp. Or a lower voltage fuse in a higher voltage fuse holder. So a fuse that rated for 300 volt, can I put it in a 600 volt system? I hope not, right? Or a fuse that rated for a 1200 amp, can I put it in a circuit, a fuse holder that rated for 800 amp? No. So that the limitation of the voltage and the current, and that limitation is done by the design. Fuse blocks, bunch of fuse blocks is these that we will go through. Anybody have seen? There's so much fuses, guys. When you have a fuse, here's the following things that you have to have label on them: the amp rating, the voltage rating, interrupting current, if they are current limiting, and also the name of the manufacturer. And the current limitation, guys, only if it's other than other than 10,000 amps. Other than 10,000 amps, if it doesn't have a label on it, it's rated for 10,000 amps. Cartridge fuses shall be classified according to the voltage and the amp rating. Fuses 600 volt or less shall be permitted to be used on any voltage up to and including 600 volt. And then this talks about, guys, the different type of, when it comes to the fuses, really the main category is, first, the voltage, is it 300 or 400 for the cartridge, is 300 or 600. Then the amps, we know the voltage in amps is easy to know. Then you get into the characteristics of them. Are they current limiting fuses or non-current limiting fuses, or are they dual element time delay fuses or non-dual element time delay fuses? So that's where you get into RK1, RK5, and the rest of the school of all these guys. Dual element time delay fuses. Two components give you a better, this is a better circuit breaker to provide the redundancy on the overload on the motors. That's why we use them. Low peak ones, non-current, you can see how they define. You can see non-current limiting rejection feature. So current limiting, so you can the current limiting and the non-current limiting have to have a characteristics where you cannot put them. A current limiting fuse, I think we're coming into it in a second here, talk about this. Here's a current limiting fuse, guys. Back to what we were just talking about, if you have a VFD and you need to protect your VFD from the energy, the magnetic energy, the heat energy, the only way you can protect your VFD if it's not rated for the available short circuit is by a current limiting fuse. So how many of you guys have seen this before? May I ask? Raise of hands, that curve. Anybody? Okay. So the current limiting fuse is, first you have to buy as a current limiting fuse. Look, really interesting. So I have my, I want to draw the line right here. Here's my disconnect. Here's my current limiting fuse. And here's my machine that bought VFD here, or soft start, my VFD or controller. And here's my machine that I'm feeding, right? So I need to protect these equipment, guys. So the way you're going to buy the current limiting fuses is, I have an 800 amp current limiting fuses. Look at the available, let's start with the available short circuit. The available short circuit current right in here, the 86,000 right in here. That's how much current I have if I am to have a short circuit right here or right here without having a current limiting fuses. If I have a short circuit without current limiting fuses, that's how much current this system is going to be imposed on. Okay, so, but there's one little problem. These equipment, my equipment here, will burn because it's not rated to handle this amount of current. So the smarter than Chad say, okay, what if you use a current limiting fuse? You go over here from the chart, and that will go up to B, and that will knock you down. That current limit fuses will knock you down to, what was the knocking down here? It knocked me available RMS. It knocked me down to 21. So now what's available down at this side is 21,000 amp, 1,000 amp, and what could come here on this side is 86. 86K. Who cares? Your chances of surviving for your equipment, you limited two things. You limited the survivability of your equipment, the VFDs, the soft start, the starters, and also you reduce, hugely reduce the arc flash that's coming out of this system. Because the arc flash, guys, is a function of the time. So you hugely reduce the arc flash. Okay, so that's the heat, that's the cooking. The magnetic force, guys, is responsible for the peak. So if you continue up here, here's how much peak you could have end up right in here, but that will knock it down because also it knocks the peak of the signal down to this value. So here's the peak supposed to be this, and now it's going to knock it down to this value. Who cares? Now the shaking of your equipment is going to be, what is it, almost 1/4 of what it should be. So you reduce the shaking and the baking of your equipment by installing a current limiting fuses. Any comments, guys? Any questions? How do they do it? They open within a quarter or less of a cycle. You know, they don't, here's a short circuit, how much a short circuit will have come. It doesn't, it opens right, start the opening right here. It doesn't allow the current to go to its full highest potential because of the ground fault. When we have a ground fault or a short circuit condition, guys, what happens is as the voltage goes to zero, momentarily, what happens if you take phase A to phase B? Your voltage going back to zero, you shunted them together, right? And to compensate for a voltage zero, what happened to the current? Shoots up in the sky. So, and that's what pushes the energy inside your building. So they cut it faster, cut it before it starts climbing up. And that's the claim of fame for current limiting fuses, and they do work. Current limiting fuses. Any current? Any question, guys, about that? Any comments? All current limiting fuses. Here's a bunch of them, guys, and how you size them. The system, if I have time, we can do a system. The system also can run a current limiting fuses, guys. These are different type of fuses that we time delay fuses and different type of fuses. I don't want to overwhelm you with these, and all these are from Busman, guys. Circuit breaker, a few things about the circuit breaker. They have to be trip free so they can turn on and off manually or automatically. Circuit breaker is indicating your circuit breaker must have an on-off position, so you know an on has to be always up if it's mounted vertically. Marking, it has to be marked with the voltage and the current, guys. Durably marked, shall be marked with the amp rating and the voltage rating to 100 amp or 600 amp, shall have an amp rating stamp. Up to 100 amp, they stamp them on it. After that, you can find it with the literature. Interrupting rating of circuit breaker, other than unless 500. So if it doesn't have a rating, it's rated for 5,000 kilo amp. Otherwise, it has to be labeled on it, shown on the circuit breaker. If you're using circuit breaker, guys, as a disconnect, they have to be, and you're disconnecting high intensity discharge, they have to be either labeled as a switch or high intensity discharge. This will tell you if you have a circuit breaker that rated for 240, you cannot install it on a system that rated for 480. But you can do the opposite though. If it's a 480, you can install it in a 240 if it fits. So series rated equipment, guys. If you have a series rated equipment, this means in the field or the manufacturers have rated certain equipment to certain circuit breaker to work together. So I have an example here. So if I have a short circuit inside this panel, and the short circuit is supposed to be 21 kilo amp, but each one of these circuit breakers is rated for 10 kilo amp. So what happens if you try to interrupt 21 when you're rated for 10? You're going to explode. What they do is they do series rated between these two circuit breakers, the main to the panel and the branch circuit. Very, very commonly used in lighting panels and receptacle panels. Not mechanical mechanical equipment panels. Typically for single phase, a lot of it is single phase, small load, non-motor load. So what happens if you have a short circuit? These two guys are coordinated either in the field by an engineer or in the factory to work together. So if the 10K if it sees anything higher than what it's capable for, it stops, and let that 22.5K here, which is the 225 amp circuit breaker, take care of business. Why it's good to use something like this? Cheap, and it coordinates up to 99% of your system. So you still have one chance, 1%, that you could trip both of them, but for the amount of money that you can save, it's an acceptable risk. So licensed engineer can do that, or you can do it in the field. Here's an example, guys, a series rated equipment. These circuit breakers are series rated, so they can, if there's any short circuit higher than what they're rated for, which they're rated for 10 right here, that big boy will take care of it. That big boy here will take care of it. If you have non-instantaneous circuit breaker, non-instantaneous strip circuit breaker, guys, the code in 2011 changed that says they want you to either provide zone selective interlocking or differential relay or energy reducing maintenance switch. So you have to have an energy reducing maintenance switch. It looks like here's a maintenance mode where you can go plug this, put the circuit breaker in maintenance mode, and set the instantaneous, turn the instantaneous on, and you screw up, in this case, you screw up your coordination. And while you are working on the system energized, when you're done working on the system energized, you go and you put your PPE, of course, right? And you have to have a reason to work on it energized, like OSHA says in 70. So you go through all this stuff, turn it on maintenance, work on it, you reduce the arc flash from this amount when you put the instantaneous on into this amount. So you can survive the arc flash based on the PPE that you have. When you're done, while you're dressed up, you turn it on so you can maintain the coordination, and you leave. So that's the maintenance solution. Otherwise, you have to have differential relay and zone interlocking. Differential relay, guys, you have to, you're looking at what's happening inside the switchgear. If there's a short circuit inside the switchgear, you isolate the circuit breaker, all circuit breakers coming to that switchgear. If you guys come tomorrow, is it tomorrow Sunday, and 3 o'clock here, we'll go over zone selective interlocking and differential relaying. That's a whole engineering terms that they use. They use them a lot in the power. Okay, we got these. I showed you a few of these. I'm gonna, for the coming guys, a couple of minutes, I gave you the short circuit calculation. Before I do that one, you guys have it here. I'm just gonna disregard that one. Go back, show you something probably you don't have. Arc flash and short circuit. Here's the system that we have. This happened to be here's a utility coming in, feeding. They have 2 generators tied to my system. I have an auto transfer switch feeding emergency panel, and all these are mechanical, electrical equipment panel. When you run short circuit calculation, guys, it's as simple as clicking here and going run short circuit calculation. Is that what you guys going to be doing in that little sheet that you have? See how easy that is? And then you come to a report like this. That's what the engineer do. And go to the text and go to short circuit report. And then you go way at the bottom. And that will give you the available short circuit. So let me show you. So right here I have okay, BB, the ducts for here. I want a main panel, switch gear. Can you just see a B is the bus? Ignore the B in front of all of them. SG is my switch gear 480. The available short circuit 3-phase is 118,000. 118,000. I have 2 generators feeding 4,000 amp to the switch gear, and the utility is pumping 4,000 amp to the same switch gear. And you're flipping the switch, you're tying them all together, phase to phase to phase, and flipping the switch. That's what you get. So in order to reduce this value, guys, you have to basically take the generators at one time and the utility at another time and see what's the likelihood that I'm running generators and I have a short circuit. Utility generator parallel together and I have a short circuit. Highly unlikely, so you might have to say, we did a project like this and we say, you know what, it's highly unlikely, and instead of going for a very expensive equipment to meet this short circuit, we're going to go for 85 because 85 will cover the utility side, and for the short amount of time that we're running generator and utility, it's a risk that you'll take and the customers will sign off on it and we move on. So that's kind of the short circuit on the switchgear. If you look at the MB, guys, mechanical panel, there's 53,000 amp short circuit on it, so I need an equipment rated for 65. Same thing for M2. Receptacle panel, look at the receptacle panel. I have only 5,000 amp on my receptacle panel. It makes sense because it's 28120, very small. You have a transformer, so in this case I can get away with what? With 10,000 amp rated equipment. The fun thing is the arc flash. So you go from there and you look at your arc flash. Here's my equipment of not equipment evaluation. Run arc flash. When you go to the arc flash, guys, it tells you, do you want to use this book? Can you get C70E right here? Or you want to use ANSI or IEEE standards. Here's the most common one that we run is IEEE 1584. So when you go hit OK, you get yourself the arc flash. You guys are probably familiar with the labels. So preview it, and let me just go take you to the labels. Here's the labels of the arc flash for every single panel in my building. Now all what you have to do now is this would be PDF file. Send it to a printing company, and they will print it in whatever background that you want it to match the environment. Look at this here, guys. This is bus. I have a bus duct that there is no PPE that you can work. Do not work on this live. If you go there and there is a short circuit, you would not go home alive. So you see a lot of places where you cannot work on equipment live. Here's another one here. CT cabinet right here. Where did it go? This is CT, the CT cabinet. Remember how you bring the 4,000 amp conductors into a CT cabinet? Where's the overcome protection device that protects it? None. On the primary of the transformer, maybe on the secondary, oversized. Look at this. It says if you were to open this one and work on it, energize, you're on your own. That's a CT cabinet. So anyway, chiller. If you're working on a controller of the chiller, you need level 3 arc rated shirt and pants. This is PPE 3. 11 calories. So you need calorie. Yeah, you need 11 calorie per centimeter. That will be, level 3. So that's a couple of things, guys, about level 4. I need a level 4 here, 26 calories per centimeter, level 4, or PPE 4 on this switchgear. So I thought just to show you these guys before. So anyway, so these are, it's so important, guys, the calculation that you see that we gave you. The software will really go through a whole lot of effort to get you to the calculation that you have just looked at here. If you don't have the fancy calculation that your friend Chad has, you're going to have the calculation give you line to line or line to neutral. This is very easy. It looks at 240 phase, guys, and you have to find how many feet. There's a 400 switch. Here's the fuse that we're using, 25 feet to 500 kcm. You have to have the F factor. There's an F factor, an M factor, and so forth. And here's an example how they do it. You find the full load current of the transformer, then you divide it by the impedance of the transformer. That will get you the value, and that will give you a multiplier, this one, and then basically divide the full load by the impedance, get you 22,000 amp. Unlimited, if you have an unlimited amount of source, will get you a 22,000 amp on the secondary side of the transformer. Then you plug it into this formula, guys, and this number here, this number is for the conductor, and 2 because it's a single phase, gives you this value. So meaning it will knock down your, because of the feeder, you will knock it down by this value. Then you plug it into the M factor. It brings you to 0.8. Then you multiply the 0.8 by the available short circuit at the secondary transformer. It gets you 18,000. Long story short, guys, what this did, it really, because of the feeder, I knocked down my short circuit just by the impedance of the feeder from 22 into 18, just by putting this feeder right in here, the 25 feet of 500 kcm. 25 feet of 500 kcm. And don't forget, guys, you sign in here. There you go. Any comments, guys? Any questions? Any comments? Any questions about that? So that's the calculation for single phase. This will give you guys the value, they call it the C value. This is the value, like equivalent to impedance, that's going to choke the current as it goes through the conductor. I always tell them, without getting too technical, guys, there's an advantage and disadvantage of being far away from the service. When you have a panel 300 feet away from the service, what's the disadvantage? Everybody knows it. Line drop, voltage drop, that's a disadvantage. What's the advantage of being far away from the service? Short circuit. The short circuit will be choked by the impedance of the cable. So 300-400 feet away, you might end up with a smaller panel and cheaper circuit breakers inside it because the impedance of the cable will choke the current. So obviously we have to find the happy medium between them. You can't win with both. So these values are supposed to get you this. For a single phase, they do the same thing as same calculation. I'm going to jump into for arc flash. Look at this. For arc flash, they use the values, guys, and they multiply them by here's a voltage phase. So to get the arc flash, and this is not. So here's arc flash. Can you guys see how for 3-phase, you take 83%. 89%, and you calculate the arc flash based on that one, 74 and 83. So these are values that they use for 480 and 280. I always bring to your attention, guys, this voltage. Can you guys see why the arc flash on a 280 system is minimum compared to the arc flash on the 480 277? Higher the voltage, the more it can push arc away from it, right? So an arc flash on the 480 is 3-4 times more dangerous and more lethal than an arc flash on a 280 120 system or 240 120 system, because you have a huge amount of voltage that can push huge amount of energy into you. Talked about current limiters, guys. This is just, they use it to limit the short circuit in certain areas. Okay, so that's basically all what I have for you guys. I don't know if we forgot anything. So, any comments, guys? Any questions? Any comments? Any questions? You got you. I want you, before you leave, guys, I have 15 minutes to get you to sign in, and I would like you to take a second to get you guys your certificate. And please, if you have a chance, just to pass this one and boot it out for the class. Thank you. While you're doing that, do not leave, please, before you guys sign in. Please do not leave before you sign in your sheets. And I'm going to get you this certificate here. Okay, how about if I pass them here? And I'm going to put, okay, or Brian, BRY1, and say right here. Dan, we have Dan here. Dan, Dan over here. G. Dan, G. Of course, so if you want to class, Dan, Rich. Let's do it. Yes, please. Need a service. Make sure you just signed in. Derek. Derek is here, my friend. Thank you. David. Yeah. Yeah, absolutely. And David, my friend here. David. Slides. David.
Ian, there you go, my friend Ian, thank you. And Donald, there you go. Thank you, my friend. How about Eric? Eric? Eric, how you doing? Grant? Eric? This that's, the law of the average, huh? James. Here. James, okay. James, Josh. Sir. This one. Okay. Another James, too. There you go. Thank you. Make sure you guys sign in, please. And Jeff. Thank you. Thank you, my friend Jeff. Neil. There you go, my friend Neil. One more certificate from your friend. That's a while. Robert. Yes. There you go, Robert. Is another Robert. Robert. No other Robert. Shane. Shane. Sean. Todd. Yes. Todd. Yep. Thank you, Todd. And Tom. There we go. That's an easy. Thank you, guys. Watch for that one on YouTube. I'll let you guys go a little bit early because I'm not feeling good myself. So, thank you. Thank you.
Yes, thank you, sir.
Thank you. Good luck. Yeah, thank you.
Just mail it in.
No,
Mail it.
you can mail them or you can leave them here if you want. If you're mad that much at me, you can mail them. Everybody got the Nivel, guys? Nivel, thank you. Please give me the. Thank you. You can leave them in your desk, guys. Thank you. You can collect them and mix them. Thank you, guys.